So this meeting is being recorded. Thank you all for joining today. My name is Kevin Delano. I'm a geologist at the State Water Resources Control Board. And today is our third webinar in our Ventura River Watershed Modeling webinar series. Today's topics are the preliminary draft calibration of our groundwater surface water model and next steps for this modeling project and how to stay involved. As a reminder, so this project is being worked on by a team from the State Water Resources Control Board and the Division of Water Rights where I work, as well as the Total Maximum Daily Load and Non-Point Source Unit from the Los Angeles Regional Water Quality Control Board, and our modeling team at GSFLOW Consultants and Daniel B. Stevens and Associates. So you'll be hearing from a few of us today. This is kind of a full list of the project team that works on this project. Normally with a meeting of this size, or any public meeting, I like to go around the table and hear who's all here. Unfortunately, due to the Zoom format and the number of people that we have here, and also the volume of material that we want to get through today, we don't have time to do those kind of usual introductions. So from the project modeling team, we'll introduce ourselves as it's like our turn to speak. And if you do happen to ask a question or unmute, we encourage you to introduce yourself too. I do include all of the water board's contact info here, so you can easily reach out to any of us at any time with questions. And this contact info is repeated at the end. If you haven't noticed already, these first few slides, this introduction is the same as I've given on the previous webinars, but I'm just going to go through it again in case there's someone new or whatever. So at the start of the meeting, all non-host participants do not have permission to unmute or turn on their video. That being said, we are running this webinar series because we want to hear from you and we want to solicit comments and questions. So during the presentations, we'll have stopping points where we'll kind of go through the questions that people are asking. So I'm going to be kind of running a queue of questions, just as I've done before, where you can, or I'll have a queue of questions, and if you want to get in the queue, you can either just type your question into the chat at any time, or you can use the raised hand feature in Zoom. That's if you go to the bottom of your Zoom window and click on reactions, there should be a raise hand button. If you're having trouble finding that, you also can just type your question type into chat that you would like to ask a question, and either way, we'll give you permission to unmute so that you can talk to us and we can talk to you. And just please remember to mute yourself when you're not talking. You will have that permission to mute, unmute for the rest of the webinar. This time around, we've got about 15 or 20 extra minutes for discussion at the end. That's shorter than in previous webinars, but that's because we've got more material to cover. And as always, we have instructions. This meeting is being recorded, and we're making the slides and the chat log and the meeting recording available. We acknowledge that it's difficult to provide comments from an oral presentation. It's not ideal. That being said, that's why we're making these meeting materials available. And so we'll have instructions for how you can access the slides, the meeting chat log, and a video recording of the meeting at the end of this meeting. Those instructions are the same as they've been for the past webinars. So if you already know how to access that FTP or view the meeting recordings on YouTube, you can just find that online. So like I said, this is the last of 3 webinars. As a review, we ran this webinar series to review the background of the project, to provide updates on model development progress to the community and to our technical advisory committee. And we're soliciting technical comments on new information. So in the first webinar, we presented revisions to geology. In the second webinar, we discussed water demand and distribution in the groundwater surface water model. In this webinar, we'll be sharing our preliminary calibration results, preliminary draft calibration results. We will not be discussing validation today. That was something we said we were going to talk about. We are not getting to it today. We're actually still working on it, and we're not ready to share that yet. But calibration itself is going to take up a lot of time anyway. So I hope there's still plenty to talk about. Also, at the end of the presentation today, we'll talk about the remaining project timeline and how you can continue to stay involved. So as a reminder, please submit your technical comments by Friday, June 25th. You can email them to instreamflows@waterboards.ca.gov. If you need additional context or questions ahead of submitting comments, you also can email any of us and talk to us, or we can set up meetings. So if you find that the meeting materials aren't enough, please reach out, and we want to provide you everything you need to give us comments. We also do record all of the questions and comments that people ask during this webinar and all the webinars, so that even if for consideration. So if you've asked a question or a comment, we are keeping that in mind and thinking about it. I'm going to wrap up this introduction with just the outline for today. So this introduction is almost over, and I'm going to hand it over to Geosyntec. They're going to talk about the preliminary draft calibration of the surface water model for about an hour. And that includes pauses for questions. We're going to break around 10:15, and when we come back, we'll talk about preliminary draft calibration of the groundwater portion of the model. So again, this is one model, GSFLOW, that has both surface water flows and groundwater flows, groundwater levels are calibrated. We've got around 15 extra minutes at the end for discussion if there's anything we didn't get to so far. And then at the end of the meeting, I'll share the remaining project timeline, so what you can look forward to in the next 12 months, and just our usual wrap-up slides. And we might go slightly over noon. I can stay past noon if there's additional questions, and we want to hear from everyone and make sure everyone can ask or say what they would like to say. So with that, I'm done. And Al, are you ready?
Yes, I am, Kevin. I'll just thanks very much. Let me share over the top of you.
I just took my screen down. So.
Great. Can everyone see the screen? So come up.
We're seeing the presenter mode, so we're seeing.
Oh yeah, I can fix that. There we go. Is that better?
Yes. That's
Great.
Good.
Thank you. Great. So as Kevin mentioned, I'm going to talk about the surface water calibration part of the GSFLOW model, and following the coffee break midway through, then Greg Schnarr at DB Stevens is going to talk about the groundwater component of the model. So while they're kind of separate presentations, the surface water and groundwater models are intimately coupled in the model. So we are working together, but it kind of seems simpler to present things kind of in this fashion. I'll point out that this webinar only covers the GSFLOW model. It doesn't cover the water quality model. So we're dealing with just flow quantities of water, not the water quality in this webinar. And again, the focus of this project is on, flows kind of relevant for fish habitat. So it's not a model designed to capture, large storm peaks and, very high volume flows. So we spend a lot of our time kind of calibrating to the lower and mid-range flows. So the outline of the next 40 or so minutes, going to talk about the calibration period. In our study plan, we propose to use a certain calibration and validation period. Following some comments from the TAC and the public who pointed out that our validation period was kind of at the back end of an historic drought and may be problematic, we kind of revisited that, and we actually shifted around the calibration and validation periods. I'll kind of go over that just to get a more representative hydrology within each of those periods. Then I'm going to talk about the approach that we take to calibrate the surface water model, talk about the key parameters that we are changing to achieve calibration. And by calibration, I mean trying to match the flows produced by the model, the in-stream flows produced by the model, matching those to gauge data. I'm going to talk briefly about the PRMS-only iterations that we did. That's the surface water model, and then move on to the GSFLOW model. And then finally, I'm going to talk about present the preliminary surface water calibration results. And as Kevin mentioned, we're not presenting the validation. We're actually still working on the calibration. There's some aspects that we're trying to improve on, that they're actively being worked on. So we don't want to get into the validation before you have finished the calibration. And I just realized my camera is not on. I had intended to turn it on. Hold on. That's odd. Sorry, I can't turn on my camera without. There it is. All right. Sorry about that. Now you have to look at my face. So moving on, first discussing the calibration period. Let me just switch this again. Okay, am I back live here?
Yep, looks good.
Sorry about that. Great. Just taking a look at the historical hydrology in the region. This is a plot from the Ventura River Watershed Management Plan, published in 2015. The bar chart shows annual runoff by water year at Foster Park, so that's kind of the lower part of the Ventura River. And you'll see there's huge amounts of variability, as is typical in California and particularly Southern California. We've got very wet years, many of them from 1930 through, this plot goes to, I think, 2013. There's periods of wet years, very wet years, and then there's periods of low years and droughts. So very challenging hydrology. And when we calibrate and validate a hydrology model, we want to make sure that both the calibration period and the validation period have representative hydrology. And this can be challenging in California. I've drawn this box here on the edge of the plot. This is where our modeling period, which is from water year 1994 through 2017. And our modeling period is kind of constrained by kind of practical limitations. There's limited data prior to the prior to about the mid-1990s. There's less data, less accurate data. So if you use it, you're going to have a less accurate model. In addition, we're assuming fixed land use in the model. If we didn't do that, we're going to have to start and restart the model, which we didn't want to do. So, assuming fixed land use for more than a couple of decades may have other limitations. So we're kind of constrained at the front end of our modeling period to about the mid-90s. And in late 2017, the Thomas Fire started, and that results in hydrological changes in the watershed that we're going to evaluate using a scenario, but we're not able to use it as part of our kind of calibration and validation. So we're kind of constrained to using these 24 years indicated in this red box. I've just zoomed in on that and updated it. We kind of downloaded the flow data and extended that same plot to include our full modeling period. So the original proposal had a calibration from water year 94 through water year 2014, and then a validation in 2015 through 17. And again, this is on the tail end of an historic drought, which would not provide a representative hydrology to validate the model. So we kind of took a closer look at this and decided that a better approach would be to revise the validation and calibration periods. So now we're going to calibrate from water year 1998 through 2017, and then we're going to validate against water years 1994 through 1997. So kind of looking at each of these, for example, there's 3 very wet years in the whole modeling period. So we've kind of got 2 of them in our main calibration period and 1 of them in our validation period. That seems like a logical approach. In addition, we've got the several wet years and dry and normal years in our calibration period. And in our validation period, we have a dry year, a very wet year, and 2 normal years. So both these periods are more representative than the original proposed periods. It is a challenge, though, with California hydrology to find kind of representative periods. The hydrology is just so variable. So again, this webinar presents the preliminary calibration results. So the results that you'll see are for 1998 through 2017. So I do have a quick break there for questions, if there are any, before we kind of move on to the calibration process for the surface water model.
I haven't seen any yet. Would
Okay.
anyone like to ask a question?
And we can come back to it at the end too. So maybe I'll move on and we'll save a few minutes for the end. So the surface water calibration approach. I'm going to talk about the key calibration parameters that the PRMS model uses. That's the surface water modeling part of GSFLOW. I'm going to describe briefly how our initial estimates for those key parameters are developed using ArcPy scripts provided by the USGS, and they provide estimates for the distributed parameters. So most of these parameters are distributed in that they have a individual value for each HRU or grid point throughout the watershed. So they're really, they're determined using GIS scripts. And a lot of that data that I'll kind of go over quickly is data that was presented in the first webinar. We're going to talk about how we scale these initial estimates of these parameters up and down based on trial and error and intuition and understanding the processes to eventually achieve calibration. And by calibration, I mean we're trying to match the predicted surface water flows with the measured surface water flows. I'm then going to talk briefly about the PRMS-only iterations. We first ran the model without the full groundwater model to kind of get things close, and then finally talk about the GSFLOW iterations. And again, I'll point out we're not working in a silo. We're working closely with Greg Schnarr and his team, because it is a coupled process between the surface water and the groundwater. So PRMS, I went through this, I think, a little bit in the technical overview in the first webinar. The PRMS stands for the Precipitation Runoff Modeling System. There's a lot of different parameters. I'm going to talk about a few of them. Here's a little schematic from the PRMS manual. It shows a couple of different storage areas within the soil. You've got a capillary reservoir, a gravity reservoir. You've got a couple of different parameters to represent those. And again, these are distributed. You've got evaporation in this parameter that you can use to calibrate the evaporation. You've got surface runoff, and there's several parameters related to that. And then you've got the flow into flow. So that's the flow where it can flow from one HRU down gradient to another HRU and eventually out into the streams. And then you've got drainage from the soil down to the groundwater model. And this rate here we found was one of the key rates when working together with the groundwater model. This soil to groundwater rate, SSR 2GW. So anytime we were working with that, we had to be mindful of the effects that would have on the groundwater and vice versa. This is just a table. I kind of pulled definitions of these parameters from the PRMS manual. I'm not going to go through it, but it's there later if people kind of want to look at it on their own to get a better understanding of what we identified as these key parameters. So as I mentioned several times, there are a lot of input parameters for PRMS, and the USGS developed some ArcGIS Python library scripts that take in different data and produce initial estimates of these parameters. And then as part of our calibration, we adjust these initial estimates to get a good match. So I'm going to go through these fairly quickly before we get on to the results. And I presented these, I believe, in webinar number 1, but I'm just going through it quickly here so it's kind of fresh in your mind. So one of the scripts is called the Cascade Routing Tool, and you give that elevation data. So we used USGS data, county LIDAR data, as well as Lake Casitas bathymetry data, and it creates a stream network, and it also calculates the slope of each HRU. And the slope is important because variables that related to the interflow depend on the slopes. If you've got a steeper slope, it's going to come up with a higher estimate. The USGS ArcPy scripts will come up with a higher estimate for these interflow parameter rates. The scripts also deal with taking rain gauge data and kind of interpolating it spatially using PRISM data, and I talked about this in webinar number 1. The gauge is the watershed is generally well calibrated, but there are limited gauges up on the ridges. I'll talk more about that later. So from that way, we get a complete spatial description of the rainfall on any given day in the watershed that the model uses. Then we have a lot of different land use, vegetation, and soil data, and this is kind of a real key part of the ArcPy scripts. They use these data and kind of, I'd say, physically based equations, but also somewhat empirical equations to come up with initial estimates for the parameters. So there's things like percent impervious, there's vegetation types, there's a lot of different soil types, whether it's soil depth, conductivities, water capacity, percent sand, percent silt, and percent clay. All these go into the ArcPy scripts to come up with estimates for these kind of key parameters. And I've kind of listed the 5 bigger ones. We did look at more than this, obviously, but these are kind of the main ones that we are playing with when trying to achieve calibration. So once we've got our initial run, we run the model, and it doesn't look particularly great, and we have to make adjustments to get the flows to match the gauge data. And so we apply scaling factors to each of these initial estimates. Remember, each of these parameters, it's not just a single number, it's a spatial distribution of numbers. So you can kind of make a map of all these of each of these parameters. So we scale them up or down. We may scale them kind of watershed wide as a whole. That's kind of how we started. And then as we got things looking better, we ended up scaling, different amounts in the mountains versus on the flat regions. And we did that to achieve, to try to match the flow rates. And we looked at results. We kind of looked at time series plots, which I'm going to show you shortly. And I think they're very helpful to understand what's going on. But we also looked at the statistical metrics that we defined in the study plan. This table 6.1 is from the study plan. I think there's links to this on the board's website. So we've got a percent average estimation error and an absolute average estimation error. And we've got different kind of goodness of fit categories. If we're kind of within 5%, we call it excellent. If we're within 10%, we call it very good. If it's within 15%, it's good. And within 25%, it's fair. And I think our goal was to get things good and above in general. We also have the Nash-Sutcliffe model efficiency. That is better at kind of describing the ability of the model to capture, I guess, the variation and the temporal trends among the data. So that a perfect model would have an NSME of 1. So again, we have different categories of goodness of fit. Greater than 0.95 would be classified as excellent. Greater than 0.85, very good. Greater than 0.75, good. And greater than 0.6 would be fair. So these will come up, or present kind of results for these metrics for the preliminary calibration. So the PRMS-only iterations. We did some PRMS-only iterations because when we first ran the model, we knew it wasn't going to be that close. So we had to do a lot of calibrations at the onset to get things close before it was even worth coupling with the groundwater model. The nice thing about this is that in PRMS-only mode, without the 3D groundwater model beneath it, it runs pretty fast, 10 to 15 minutes. So we could set up scripts and batch processing to run a whole bunch of cases all at once and make little plots of the statistics as a function of scaling parameters, and use that to kind of hone in on an initial calibration. This was an iterative process, as is the full calibration. We did this just to kind of get the high flows correct, because it doesn't really have a correct interaction with the groundwater. But it was helpful for dialing in the high flows before we moved on to looking at the full model. When we looked at GSFLOW iterations, that model takes much longer to run. We're coupling with the full 3-dimensional ModFlow model underneath. Typical runtime is around 15 hours. So it's a lot more difficult to kind of run scripts, and you'd be waiting a long time. So we kind of use more judicious selections as we just from previous model experience, you kind of know which parameters to move in which directions for the most part. So we kind of used more judgment in terms of trying to achieve calibration. when we moved to the GSFLOW model, there are additional very important processes that had to also be considered in the calibration. Clearly, we've now coupled it with the full groundwater model, and that allows a more detailed description of the surface water and groundwater interaction. And so there's some other parameters that we have to adjust, particularly at the low flows. We found that the riparian evapotranspiration along the streams was particularly important once the flows gotten very low, like below 5 or so CFS, the amount of ET from the riparian vegetation, such as arundo, became important. And then the key kind of interaction parameters, these are the parameters that if either the surface water model has changed or the groundwater model has changed, we have to be mindful of how that was affecting the other model. So the key one of the key ones is the rate that the water goes from the soil into the groundwater. That's obviously one of the direct links between the two models. The horizontal and vertical conductivities of the alluvium bedrocks were important for the low flows, as well as obviously being important for the groundwater model calibration itself. So we have to work very closely with Greg as we calibrate those, and also the stream bed conductance. How easy it is for water to discharge from the ground to the stream and vice versa, leak from the stream back to the groundwater. And the groundwater extinction depth, that's how we model phreatophytes. We can tell the code around streams to enable evapotranspiration directly from the shallow groundwater, and the depth to which we enable that is how we represent the phreatophytes such as arundo. And we found that to be, although it's a mod flow parameter, it was a key parameter for the stream flows, again, particularly during the low flow periods. So before I get on to the results, we've kind of gone over a lot of these inputs. There's some uncertainty in some of these inputs, and it's worth considering that before we jump into looking at results. So I'll describe each of these in a little more detail. The precipitation inputs, it's a key driver for any hydrology model is the precipitation that you put on it. We've kind of used I think one of the best practices of using gauge data and then spatially interpolating it using the PRISM data. And the watershed is reasonably well gauged, but I mentioned earlier that there are not a lot of gauges up on the ridge lines, and that's where most of the rain can fall. And so we're really relying on the PRISM data to extrapolate from the gauges up to those ridge lines. And there may be some limitations on that, particularly as we used PRISM 30-year normals from 1981 through 2010. And we know in our modeling period, we had this kind of, historic drought from 2012 through 2016. And it's not clear whether the precipitation patterns during those drought years would be the same as during, more normal or wet years that would actually dominate the PRISM, the PRISM 30-year normals. So, for example, I think the PRISM 30-year normals are going to be dominated by the big white rain producers, like the atmospheric rivers that come in off the Pacific. Whereas in the drought years, the storms may be from a different direction. I think they typically come more from the north and have less rain. So they may have different orographic patterns. That's one uncertainty. I mentioned the vegetation and soil properties. There's uncertainties within that. They may not be that important because they're really just used to provide an initial estimate, and then we can kind of calibrate some of those uncertainties out to a certain extent. There's the arundo. I've mentioned that these phreatophytes are very important at low flows. We had some arundo data from a 2011 report, that kind of spatial data, and I believe that was from a 2007 survey. There's since been eradication efforts. Some have been successful, some maybe less successful. So there's a bit of uncertainty as to where the arundo is. And also the density of the stands. And again, we're running a 24-year model with a kind of fixed assumed land use. So where the arundo may have been at the beginning of the modeling period may be different to where it is at the end. So these are other sources of uncertainty. I mentioned the fixed land use. we assumed constant land use in our 24-year modeling period. This may have some limitations. We did kind of check that it didn't change drastically, but there could still be some effect of that. And one of them could be if crops have been fallowed or additional land has been turned into crops during the modeling period, because that can affect some of the demand estimates. And webinar number 2 focused on the supply and demand analysis, and that's another source of uncertainty. That was used to back out pumping flow rates, which obviously go into the groundwater model, and these can have effects on some of the gauges during low flows. There's reported diversions, so there's about 30 reported surface water diversions in the watershed. We have their self-reported volume data. Some of the numbers we saw don't make a lot of sense. They're only reported, I think, from 2010 onwards. So there's definitely uncertainty in how much water is diverted directly from the streams. There's also non-reported diversions in use, so illicit diversions. They're hard to get a handle on. We did look briefly as to whether marijuana growth was a big player in the watershed. We decided it probably wasn't, compared to some of the watersheds further north. But these could be a use of water that is not in the model, and particularly during the historic drought years when people may have been desperate to keep crops or just their backyard alive, they may have gone to additional measures. And then the final one is the accuracy of the flow gauges themselves. These become, it's difficult to measure flows in natural channels. Most of these gauges are in a natural alluvial channel that can move around. Following bigger storm, it can completely move the channel around. Now the folks maintaining the gauges, the USGS and the county primarily, they'll go out and remeasure it periodically throughout the year. But there's still a lot of uncertainty in the gauge accuracy, and particularly at the low flows. Particularly in the summer, you've got a pool of water where maybe it barely has any flow through it, and they're trying to measure the flow by measuring the depth of that pool. There's not a good hydraulic control. And in addition, in some gauges, particularly Foster Park, there's a lot of recreation in the summer, and people actually build rock dams, and that can, even changing the water level if an inch or two can really change the flow rates that are measured by the gauge. So there are a lot of issues with the accuracy of the flow gauges at the very low flow rates. So I'm going to take questions there before presenting the preliminary calibration results. Do we have anything?
Yes, I've got one from Ali Dashtigi. I'm sorry if I mispronounced that. Was there a specific sampling algorithm used to generate the parameter sets? I think this question was related to precipitation based on when it was asked. But Ali, would you like to clarify? Or I can let you unmute if you'd like. And I got a raised hand from Brian Bondi.
I can perhaps describe a little bit what we did with the prism, if that helps.
Yeah, let's go back to that. I think that was the source of the question.
Yeah, we used the published prism 30-year normals, which...
Sorry, let me interrupt you.
Kind of
the question,
yeah.
It is about the calibration parameter sets. So was there a specific sampling algorithm used to generate the parameter sets for calibration? I'm
not sure I fully understand the question, but the USGS ArcPy scripts have, if you open that, you can look at the equations. There's equations that take in different soil properties, and it'll come up with estimates for the different parameters. I'm trying to think, for example, the amount of storage in the capillary zone, if I remember correctly, was kind of equal to a rooting depth. The rooting depth, they might have related to the vegetation type, and then they took it equal to the rooting depth times the available water content. and that gives you a certain number of inches of storage in that reservoir. Other things like the rate parameters might depend on how much sand versus clay you have in the soil, as well as the slope. So there are algorithms. If you go to the GitHub link that was on the slide, you can download those. You can download the scripts. I don't think there's, I hadn't seen anything that published the actual equations they use, so you kind of have to dig through the code. But you can do that. I don't know if that answers the question, but.
I think I'm on mute, right?
Oh,
Yes.
There you go. Yeah.
Yeah. Thanks, Al, for the explanation. I think what you referred to generates the initial values for the parameter, right? The distribution
Correct.
over the space. And then you iterated on each of those parameters, right? I was wondering more, what was the procedure to generate those random parameter sets to check the performance of the model on each iteration?
Right,
Did you use like a specific algorithm or just manually change those?
No, we did it. We did it manually. We thought about it. We kind of thought we had to be pretty judicious once we got to the GSFLOW stage because the run times are so long.
Okay.
So we didn't invest time in an algorithm other than our minds, I guess.
Okay.
You know, we did spend a lot of time looking at plots of error metrics versus the different parameters. But then we'd try to, every time we look at a batch of runs, we wouldn't just look at optimizing one parameter. We'd kind of look at optimizing three of them, you know, two or three or four of them together to get a new base run.
Okay.
It was challenging.
Yeah, exactly. I mean, that's why I asked, because usually these highly parameterized models is very difficult to calibrate just manually. But
Yeah.
Okay.
Yeah.
Thanks.
Okay.
Sure.
Our next person in queue is Brian Bondi. He raised his hand, so I'm going to ask him to unmute.
Good morning, Al and Kevin. Can you hear me?
Good morning.
Yes.
Yes.
Good morning.
Hi, thank you. I just have a question about how riparian vegetation phreatophytes are being simulated in the model. Going back to your, way back to your study plan, it says that riparian evapotranspiration will be handled using the PRMS component of GSFLOW, so the surface water component. But listening to the presentation today and the discussion of the extinction depths and things, it sounds like perhaps you're also using the EVT package in the ModFlow component of GSFLOW. So I'm just looking for clarification on how riparian evapotranspiration is being simulated, because again, the study plan made it sound like it was exclusively being handled by PRMS. Thank you.
Yeah, great question. So I guess the answer is both parts are used to simulate it. In the PRMS part, we do increase the I guess if you call it a crop coefficient to represent the additional evapotranspiration, particularly for the rundo, which can be upwards of 20 feet per year of ET. So we change the crop coefficient where we have a rundo to increase the ET, and that's done in PRMS. And then we do, I'm not sure the package in ModFlow, but we do set an extinction depth that you know, on the order of 10 or 15 feet that then lets those phreatophytes actually access the shallow groundwater. Yeah, we found when we didn't do that, the PRMS wasn't doing the right thing, so we had to also use the ModFlow piece. I'm not sure if does that answer your question. So I guess we have improved upon what we said we'd do in the study plan, I guess is another way to say it.
Okay. Thank you, Brian. We have one more question from the chat from Bram Surku. I apologize if I mispronounced that too. Did you use visual observations of dry and wet reaches, assuming these were available for surface water calibration in addition to data from gauging stations?
Great question. We haven't yet. We're still kind of, we're still getting our flows kind of closer to where we want them to be, and you know, working with the groundwater part of the model as well, particularly at the low flows. But that is one of the things we'll do. We have, and I think my last slide may mention that at the end, but yeah, we have wet dry observations from Casitas and I think CDFW.
Also from Minor Soaks Water District.
Right.
I
Yeah.
think, sorry, can I jump in for a sec?
Yeah.
I'm aware of 4 agencies in the watershed that collect that kind of wet dry mapping data. That's Casitas, Minor Oaks, the OBGMA, Ojai Basic Ground Arrangement Agency, and CDFW. And of those, we asked all 4 for their wet dry mapping, and I believe we got it from Casitas, Minor Oaks, and CDFW. Does that answer your question, Bram? Okay. And are there any last call for questions before we move on? Anyone else? Okay. All right. Thank you all.
Great. Thank you. So the surface water calibration results, mostly going to focus on comparisons with the flow gauges shown here in this map. And yeah, in the future, we're going to pull in the wet dry mapping from the different agencies. So primarily, we have plots of time series, we've got flow duration curves, we've got Streamflow Statistics, the ones defined in the study plan. We've got kind of seasonal volume areas as well as annual volume comparisons. Mostly I'm going to focus on the gauges in the Matilija Creek up here, and then down through the Ventura River, as well as the San Antonio gauge. We haven't spent a lot of time working on the 2 gauges above Casitas. I've also learned that those gauges have access issues. They're not kind of calibrated frequently, and but we will come back and look at those in more detail later. And then finally, gauge 649 is a new one that was installed very near the end of the modeling period, so there's just very little data. So we're not going to present results out there either. So primarily starting up in Matilija Creeks and then down the Ventura River and also the lower part of San Antonio Creek. So this is a plot the Matilija North Fork, gauge 604. I'm going to show several of these. I'm going to spend a little bit of time talking through the first one, so hopefully the rest of them will make a lot more sense. The upper frame is just daily stream flows plotted as a function of time it's over the entire modeling period. We've only plotted the simulated for the actual calibration period, and we plotted on a linear scale. It's tough to see, but we kind of capture get the main storm peaks. But again, the focus of this model is not the kind of daily peaks and the storm flows so much as the base flows and the flows more relevant to the fish. So we've spent a lot of time focusing on monthly average flows, and that is what is plotted in the middle frame. And it looks quite different because we used a logarithmic scale. So it's able to kind of show what's happening at the low flows as well as the high flows, and I'll talk more about that shortly. And then we have a flow duration curve, which is a common way to present stream flow data, which is percent of time that a certain flow rate is exceeded. And all the plots, the measured data is in black, and the simulation results are in red. Just kind of zooming in on the lower plot here, so you can see a little more clearly what I mean by the logarithmic scale. At the low end of the range, we've got 10 to the minus 2 CFS, so that is 0.01 CFS, so very low flow. And we'll go all the way up to 1,000 CFS. So each kind of increment, the flow goes up by a factor of 10. And the reason we do this, it lets us kind of look at the whole full range of flows in a little more detail. The flow duration curve, so again, it's a common way to present both streamflow data and also to compare model results to it. So what does it mean? Well, if you look at this 10%, it means that 10% of the time, the flow rate of about, a little over 10 CFS is exceeded at this gauge. This is up in Matilija. Or if you look at the 90%, it's saying, 90% of the time a flow rate of about 0.3 CFS is exceeded per the data. So that's what these flow duration curves can show us. And again, we're not going to focus on these high end flows. It's really these kind of flows in the mid range. And I will point out as we get to these low flows, these flows are very, very low. Like, what does it even mean to try to measure a flow to 0.01 CFS? It's not going to be accurate down there. And in fact, for this gauge, you can see that they only report to the nearest tenth of a CFS. Now, that doesn't mean they're accurate to a tenth of a CFS. I think the gauge accuracy is at these low flows in a natural channel where the water is barely moving, in a rocky channel, is the accuracy of those is somewhat low. And I'll talk more about that shortly. I'm going to zoom in on the middle frame now. This is the monthly average stream flow. Again, as a function of time, black is measured, red is simulated, and we get a very good agreement. The ups and the downs match pretty well for the most part. But I just kind of wanted to use this to highlight an example of the low flows that we are dealing with. If the gauge is, for example, I picked a month in 2013, the gauge is predicting or is measuring a flow of 0.2 CFS. Again, the accuracy of that 0.2 CFS is, they only report to the nearest 10th CFS. It could be 0.1 CFS. It could be up to 0.3 CFS. But the model at that time is predicting 0.4 CFS, which I think is actually a very good prediction. They're both low numbers. But if you calculate the percent difference between these numbers, it shows up as 100% difference, which sounds high. So this needs to be kept in context when we're looking at volumes in the summer or flows in the summer. These large percent differences may actually represent relatively small absolute flow volumes. In this case, a difference of 0.2 CFS. So this is worth keeping in mind as we look at other results as we go through this. And so the couple of issues that key. The accuracy of the gauges itself gets questionable down at these very low flows, and and this can kind of magnify the relative errors of the model, even though the absolute errors may be very small. So just moving around to other parts of the watershed, I'm not going to spend as much time on all of these, but this is gauge 603 upstream of Matilaha Reservoir. I think the gauge only came online in 2003. They had some issues with it, got washed out. It's maintained by the USGS, this gauge, but the county told us that it is a little bit of a problematic gauge, but they like to have it for their flood control purposes. So really not for low flow measurements. The county really wants it for flood control. We get pretty good agreement of the model. We're not capturing the full extent of the drawdown and the drought, but again, we're deviating at relatively low flow rates below. The data shows 0.1 CFS. The model shows, maybe a little around 1 CFS. So again, the absolute volume differences in flow are relatively small. And again, the accuracy of the gauge is questionable once we get down to these low flows. Moving downstream, this is gauge 602B, downstream of Matilaha Reservoir. Kind of similar to 603A, pretty good agreement with the temporal trends of the monthly. Do not fully get the drawdowns, but again, we're dealing with very low flows. The flow duration curve matches pretty well down to maybe 1 or 2 CFS. It starts to deviate from the measurements. This is downstream at gauge 607, which is immediately downstream of the diversion where CMWD diverts water from the Ventura River through the Robles Canal to Lake Casitas. We get pretty good agreement of the trends. One thing we do note is that the gauge data frequently predicts zero flow at this location, and our model does not go down to zero. It gets down to a CFS or so. And the reason for that is we don't have the hydraulic details of that diversion structure in the model. So in reality, if you go out there, there's a berm and there's a gate structure in the river channel, and the bottom elevation of the gate structure is raised above the river channel, so that water coming down the stream has to actually pile up or build up a certain head before it flows through the river channel. So I think in reality that forces a lot of the flow underground. We don't have that detail in the model. We're not doing a hydraulics model. We're doing a hydrology model. When we get down to 608, you'll see that this effect up here does not really continue downstream. And that's because at 608, the flows there are really driven by groundwater coming back up. So it's a different thing going on. This is gauge 605A and 605. They just moved the gauge at some point. And again, we see very good agreement between the model and the data. We capture the high flows, these mid-range flows, capture these peaks. Again, sometimes the model predicts zero flows. Oh, sorry, the data indicates zero flows, and the model doesn't go all the way down to zero. But in this case, in the drought, we're getting below 0.1 CFS, which it effectively is zero. But again, if we calculate a model error at this time, a relative error, we've got 0.1 CFS divided by zero. We've got kind of infinite error. So this kind of again illustrates some of the issues with calculating relative percent errors during low flow periods. But generally, good agreement with the data. And the final gauge is gauge 608, which is the Ventura River at Foster Park. Again, good representation of the trends, capturing some of these low flows, maybe over-predicting in a couple of years the extent of low flows. We've got some higher flows in the winter and the drought years, which we're still working on. Pretty good agreement of the flow duration curve. They start to separate, somewhere around the 5 CFS range, but we're still working on this. The flows in this range are, largely driven by groundwater coming back up, forced up by the bedrock underneath it. And they're also influenced heavily by the phreatophytes in the reach upstream as well. So there's a lot going on there, and we are still working on it. Kind of switching to the metrics, this is the table we saw before. I'm not going to go into detail. In the next few slides, I've color-coded it to make it easier to kind of see. So first, looking at the color codes, the goodness of fit categories. Dark green is excellent, mid green is very good, pale green is good, and this kind of pale yellow is fair. If it's not colored, then it means it's outside these range. So I've got results for these 6 gauges. The first column is the percent of observed missing data. So 603A didn't have a full record, so about a quarter of the record is missing. 604, 1 year was missing. I guess the gauge got damaged and they took a year to reestablish it. But generally reasonably complete data. The first 2 columns with the colors are the monthly, the percent average estimation error and the absolute average estimation error. And we can see, most of the gauges, 4 of the 6 gauges are in the excellent category, very, very low volume errors. The gauge downstream in Matilaha and the Ventura River are on the high side, but still in the good to fair categories. We are working on those, particularly, both of them are high. So maybe there's an issue with, maybe there's some releases from Matilaha Dam we haven't figured out. But we're looking at that. The Nash-Sutcliffe model efficiencies are all pretty good. They're all greater than 0.9, except for the gauge 602B. And with 602B, so the NSME really measures the ability of the model to kind of capture the variations in the flow. And so maybe if we don't have, historically, Casitas would manually release from Matilaha so they could divert more water through the Robles Canal to Lake Casitas. They stopped doing that at some point, but at least the first part of our model that was happening, and we don't have data on those manual releases. So that could be a reason why we're a little lower for the NSME here, but 0.77 is still good. And 608, we're at 0.97, which is excellent. Going to seasonal volume errors, again, the same 6 gauges. The first column is the same number, percent missing, which I discussed previously. And then we've got volume errors broken down into seasons, winter, spring, summer, and fall. Again, they're color-coded. You can see typically very good to excellent volume errors in the winter and also in the spring for the I guess these key gauges, the Foster Park and San Antonio Creek gauges. Again, the 602B and the 607 gauges are a little on the high side. We've got, fair to excellent errors in the summer up in Matilaha, and then the errors get larger as we get down into, these lower errors, on the order of 50%. So we're 50% too low in the summer. But again, this is partly due to there's several things going on here. There's the fact that the flows are very low. So it's very hard to calibrate a model to flows that are close to zero. So these, although they look like large percentage errors, they're actually, relatively small absolute errors. And then finally, the full volume errors are all in the fair to very good or even excellent categories. The next series of plots kind of illustrate the seasonal volumes in a different way. This is a gauge 604 up in Matilaha Creek. The measured volumes are in gray and the simulated volumes are in this orangey red color. And this is for the 4 seasons, winter, spring, summer, and fall. We kept the axis scale the same here to kind of illustrate, I guess, the challenges of trying to have a model that can capture these full range of flows. But, generally you look at this and you can see that, we're capturing the interannual trends very well between, the simulated compared to the measured data. If we go to 603, this is above Matilaha, similar trends. Remember, the data here didn't start until 2003, so we don't have data for the first few years. So similar agreement with the model, matching the simulations matching the measured data pretty well. I will point out here, 2005, we've got good agreement. This was a very wet year. It's about 100,000 acre feet was in that year was measured going into Matilaha, and the model predicted a similar number. However, when we go downstream at gauge 602B, that same year, we've got a bit over 100,000 in our simulation, but more like 50,000 in our measured data. So this points to a gauging issue to me. I don't know where that 50,000 acre feet of water would go otherwise. The storage volume in Matilaha is I don't know, back then it was probably 1,000 or maybe a few thousand at most, and now it's close to zero. So this points to me as to being a gauge error, and this could be impacting our volume statistics as well. So that's something we need to kind of take a closer look at. It could partly explain why our overall volume statistics are too high. It's because of this 1 year. 607, similar trends. We get similar agreement. Maybe there's issues with measurement in that wet year. That wet year 2005 was the same year where the pumps at Foster Park, owned by the city of Ventura, got damaged, and they had to really curtail their pumping because of their damaged facility. So there was a lot going on in that particular year. Similar at 605, similar trends. The model's able to replicate the volumes pretty well, and same at 608. And the last plot I'm going to show is kind of the simulated annual volumes on the vertical axis against the measured annual volumes on the horizontal axis. There's different colors for each of the gauges, and there's 1 point for each water year. So about 20 points for most gauges. And we plot it against the one-to-one line. We see we get a pretty good agreement. There's a couple of outliers that maybe that's, like we can look into that. But and then if you look here, we calculated individual R-squareds for the gauges as well as an overall R-squared, and they're all greater than 0.9, except for the two gauges I mentioned above Casitas, which we're still looking into. That's it for the results. I guess, you know, the next thing we're gonna continue to improve the calibration period. We really want to get that dialed in before we validate. That's, you know, how you're meant to do it. You calibrate and then you check it against the validation period. We're also going to, as brought up the questions, we're going to make comparisons to the wet-dry mappings. This is an example of one. I think this is from Casitas, which shows, you know, I think this is a dry year. This is during the drought where, you know, a large portion of the river was dry. So we're going to make comparisons of the model to those. Then we're going to check the validation period. Hopefully we're good. And then we're going to, well, let's say we're going to do a sensitivity analysis. I mean, the whole calibration procedure is in some sense a sensitivity analysis, but we're going to kind of formalize that and make some systematic changes to the final model run and then present results so that people looking at it can understand, you know, the effects of changes to different parameters. So that's all I have. Any questions before we run for coffee?
Sorry, I got to hold you here for a minute now. First
Sure.
question, and only so far. So yeah, folks, please raise your hand or ask questions or type that you would like to ask a question in chat. We'll let you unmute. Okay, first question from Ali. Sorry if I mispronounced that. Were the error statistics calculated excluding the observed low flows that showed high errors? Also, was the model calibrated separately for dry and wet periods to see if it will improve the dry period results? I think, Ali, you can unmute yourself if you want to.
Thank you.
Yeah, no, good question.
Yeah, go ahead, Alex.
Yeah. The first question, we didn't exclude anything in those statistics we presented. We are thinking about that. You know, if we, you know, below a few CFS, there's a lot of uncertainty in the measured flows. So that might be something we consider is excluding those from the statistics. I'm worried if we do that in some years, we won't have any data left in the summer because it's all low. So that's a good point. And what was the second question?
Well, basically, I was wondering if you have calibrated the model separately for dry period compared to wet period to see if the dry period calibration would improve.
No, we didn't. We looked at the whole calibration 20 years. I mean, we're kind of doing that. We're looking at the time series plots. We're kind of doing that because there you can very clearly see the difference between wet periods and dry periods. But it also shows up in the the Nash Sutcliffe, and our initial model runs. Was struggling to capture the full range of behavior that we see in the model now and that we see in the data. It wasn't capturing the drought, and so we had to spend adjust numerous parameters to get it to capture the drought, and that's part of the importance of having different hydrology in the modeling period, that you want to capture both parts of it. That's right.
I mean, I was wondering if you were able to probably, if you want to improve the dry weather flow simulation, have a separate parameter set for the dry period compared to another parameter set for the wet period, because you said that probably the focus is going to be on low flows a little bit here for the environmental purposes. So
yeah, that would be an option, I guess. Some parameters have less effect on the dry period than others, so we use those for the wet period, So you're saying, sorry, for wet years versus dry years, like normal years versus drought years, or are you saying for winter flows versus summer flows?
Yeah, for the years that you are not able, like you said, that we have low flows that model does not do a good performance in capturing those low flows. I was wondering if you could probably separate those, like a dry weather model and a wet weather model, something like that.
Or do adjustments for the drought. I mean, that was an historic drought. And we've thought about that. I guess we try to do it without doing that if we can. But also getting back to one of my other points is the precipitation patterns may have been quite different in those years. I mean, I remember there was this big blob of warm water in the Northeast Pacific, and it was kind of changing it was basically sending all the storms around California. But the ones that did make it in would travel around the high pressure and then drop in from the top. And I think they have very different orographics than, the Pineapple Express that comes in off the Pacific, which probably dominates the 30-year normal. So that's another thing, is like if the rainfall was less than, 10 inches in Ojai, do we assume there's a different set of orographics? That may be something to consider.
Thanks.
Thank you for those questions. I'm going to move on to the next question. This is from Bram Circu, and I'm going to give you permission to unmute. So Bram asked, does the preliminary draft calibration simulate low but continuous surface flows between gauges 607 and 605 during the summer? I do understand that you're still working on that part.
Yeah, I think that's going to be illustrated better in the wet dry mapping that we're going to work on once we're happier with the gauges. I mean, the gauges look pretty good, but there's a few things that we're working on to improve it. And so I think I'd have to look at the model results in terms of when it is continuous and when it is not. But I think the wet dry mapping is going to show that pretty clearly. Does that answer the question? So I guess the short answer is no, we haven't looked at that in great detail yet.
Okay. The next question we have in chat is from Christian Labor. Number 1, what ET values were used for Arundo? Number 2, how was the model adjusted to reflect changes in riparian vegetation distribution and density that occurs in the seasons after high flow events? Let's do number 1. What ET values were used for Arundo?
I'd have to check my notes. I believe it was 20 feet per year. It may have been 24. I'd have to check, but I think we used a number from the 2011 report. And that may be something we look at in the sensitivity analysis too, how important that number is. Second question, changes in vegetation after.
Sorry. How was the model adjusted to reflect changes in riparian vegetation distribution and density that occurs in the seasons after high flow events?
Yeah, we haven't made any adjustments. We've got a fixed land use in our model.
So there was no adjustment to the removal of vegetation that occurs during these extreme events, and no analysis of the change that occurs as that vegetation grows back in the riparian zone?
No, I think that would involve having a model with changing land use. It would be fairly complex. It might, that's obviously another source of uncertainty that I kind of touched upon with the extent of Arundo, and how that was fixed in the model, and it may be changing. So that's another good example. So maybe we look at following years with big, large storms. If our low flows are too high, maybe that's a reason. If we don't, if our low flows are too low, that might be a reason, because if we didn't remove riparian vegetation, then that could be another reason. But I think that's I think that's a tough thing to start changing those things over time.
Yeah, I also.
So we are,
Oh, sorry.
no, go ahead.
I also, Christian, I also wonder what data is available that shows that captures those changes.
Google Earth.
Yeah.
Any set of aerial photos.
Okay.
Yeah, I think we kind of settle on a fixed land use, and it's a tough one because when you come into run scenarios, are you going to make an assumption that every time a storm is greater than X, you start removing the phreatophytes from the domain? It's I guess you could, but it seems like a tough one.
Yeah, I understand it's a mathematically complex exercise, but from a ground level perspective, when you go river depth from less than a foot to 20 feet, in that range of Foster Park, and see the effects and what happens in the years following years like 1998 and 2005, there is a tremendous change. And given that vegetation, as he quoted, removes 20 to 24 acre feet per year, and there are probably in the order of high tens to possibly hundreds of acres of arundo and riparian vegetation. That change is bound to have a profound effect on water levels and flow in the watershed.
Al, this is Brennan. I think we're going to be exploring the effect of this and reporting on it in the fire scenarios. So some of this will be captured there.
Okay. I have a couple. I think we're going to take a break here in a second. So thank you, Christian, for those comments, questions. We have 2 comments in the chat that I'm just going to share because they're related. Paul Jenkins writes, this issue has been explored in the algae TMDL analysis. And Regina Hirsch writes that Ojai Valley Land Conservancy is mapping arundo in the watershed right now with a current extent of near 70 acres. So thank you for those comments. And I think we'll take a break here. So we'll be back in about 5 minutes to discuss preliminary draft calibration of the groundwater portion of the model. So thank you for these questions. If you have, if you have a new question or whatever, just drop it into chat or raise your hand. And, all right, thank you all.
Great, thank you.
Hello, folks. We'll be starting again shortly. Greg, would you like to pull your screen up?
Sure. I'm also turn my camera on.
Hello.
Hi. How does that look?
Looks good. I think we'll get started in just another minute here. We are recording again. So thank you, Al, for that presentation, and thank you everyone for these questions. I expect we're not done talking about vegetation. We did get another comment in the chat from, I'm sorry for mispronouncing your name, Eulina Mukowska. I'm sorry for mispronouncing that. Eulina wrote, exploring this issue during fire scenario analysis, as mentioned by Brandon, with geosyntech seems insufficient. So thank you for that comment. I will start at 10:25. Okay, take it away, Greg.
Yeah, thank you, Al and Kevin. And I'm going to spend about an hour discussing the deeper portion of the model domain, the groundwater primarily. And I'm following a similar format than Al. I'm going to talk about our approach, and then I'm going to present the preliminary draft results of the calibration. So when it comes to the approach, I'll discuss some of the key parameters that are adjusted during calibration. I'll kind of go back and review the different zones spatially that were established and we actually talked about previously in an earlier webinar on the geologic analysis. I'll discuss how the initial conditions of the model are established for groundwater elevations and then the various different boundary conditions, a little bit of background on how GSFLOW works, and then I'll present the calibration statistics and goals that we set out to achieve and that are documented in the project study plan. And just like Al did, I'll sort of go through what I see is what we see as sort of some of the key input and data limitations. So when it comes to the input parameters, I'll start sort of where Al left off. This list on the left is a list. It's not comprehensive, but these are really the key parameters that we have been adjusting within reasonable ranges as we try to achieve calibration of both the surface water and the groundwater model, part of GSFLOW. So Al showed this diagram, and so this is one of the key parameters is SSR2GW rate, and that is a GSFLOW parameter that it has a large influence on the amount of recharge that enters groundwater from precipitation and irrigation. And as Al mentioned, we all have to coordinate very closely, and this is actually why this is a much more challenging exercise than traditional groundwater modeling, because every change that we make, we have to be careful that it's also working towards achieving the surface water calibration. Now, this diagram I'll have on the next several slides, and it is from the GSFLOW manual, and it is a sort of a cross-sectional spatial representation cartoon of the different parts of GSFLOW. And the kind of solid black lines are the bottom or the totality of the PRMS surface. And so everything Al was talking about is happening in here, really. And he's also looking at the output in the stream. So now we're moving deeper, and these grayer areas are really part of the ModFlow portion of GSFLOW. And so the next several parameters I'll talk about relate to this deeper zone. So the first is underneath the soil zone within GSFLOW, there can be an unsaturated zone. So there's an additional zone between the soil and the groundwater saturated zone that is the unsaturated zone. And as this dashing indicates, that boundary is actually computed by the model. That can change based on groundwater elevations. And there are several parameters that dictate that unsaturated zone, but the key one is the hydraulic conductivity, or the VKS. And that would dictate, percolation from the soil into the unsaturated zone, as well as recharge from the unsaturated zone into the saturated zone. So that's a parameter that also has influence on the surface water modeling. The next is the stream hydraulic conductivity. And I'll talk a little bit more about the Streamflow routing package, but this is how a stream is sort of represented here. And in addition to direct input from the soil zone, we and a very important component of this watershed and of this model is the interaction between the groundwater and the streams. And so that is really dictated partially by the stream bed hydraulic connectivity. So that's another key parameter that influences both recharge from streams and discharge to streams. And then the last two are really the more traditional standard groundwater calibration parameters. And that's the aquifer hydraulic connectivity first, and that's what all these arrows represent. These are the aquifer properties, the hydraulic connectivity of the saturated portion of the groundwater domain, and it dictates the rate of groundwater flow between different model cells, different areas of the model, both horizontally and vertically. It also has some bearing on the amount that can percolate in from the unsaturated zone, or the soil zone, or the streams, or the lakes. And so this parameter, all of these parameters vary spatially. So they're not the same throughout the entire domain, vertically or horizontally. And the last is the storativity, which is also a property of the aquifer, the saturated portion of the domain. And that dictates the response of groundwater changes in elevation based on changes in storage. And so it's a representation of how much groundwater can be stored with any certain unit of volume unit of the aquifer media. So as we're calibrating the model, these is a list of what we've been focusing on. And like I said, this varies spatially, vertically. So we're adjusting these parameters, and the initial values of all these parameters are based on available data from the watershed, where available, and otherwise often on literature values. A little bit of background and review. This goes back a couple of webinars, but when I talked about how all of these parameters vary spatially, the way that we achieve that is to begin with this zoning, where we establish different zones within the three-dimensional domain, horizontally and vertically. So what we're looking at now is the very top domain. So the numbers increase as you go deeper. So this is layer 1 of the GSFLOW groundwater portion of the domain. And so this represents the top of the saturated or unsaturated zones within the groundwater where they're present. And these zones were based on the geologic analysis we talked about a couple of webinars ago. And so, for example, where there are shale units present versus sandstone, those are different zones. Different geologic mapping of alluvial of alluvium. We started this entire modeling exercise with the calibrated Ojai Basin groundwater model. So we started with the zones that had been established from that calibration. So there's a lot of different reasons why we've set up this zoning and it looks the way it does. And as you move vertically downwards, many of the alluvial sediments are thin, less than 100 feet or so within large parts of this watershed. So as you move deeper, some of the alluvial sediments are no longer present. And as you continue to move deeper, it's really only the Ojai Basin that has these sediments for the most part that are hundreds and hundreds of feet thick. And so we did simplify the layering in our initial Ojai Basin groundwater model. That model had, I think, 10 layers. It is somewhat simplified now for this regional scale model, watershed scale model, to be 7 layers now. So this, as you move vertically downwards, this is the bowl shape of the Ojai Basin that's kind of getting narrower and skinnier as you move down. So each of these different zones is assigned, can be assigned different values of each of those parameters that I listed previously. So the next step is setting up initial conditions. And as Al discussed, the initial, the model period runs beginning from the fall of 1993. And so within the alluvial portions of the watershed, the Bolton 118 basins and San Antonio Creek Corridor, Lion Canyon Creek Corridor, we did establish these initial conditions based on measured data from observation wells that are present in the watershed that are shown on this map. So there are, as we'll talk about more, really when we're focusing on calibration, we're talking primarily about data that's collected by Ventura County at about 60 wells, 60, depending on what time period you're looking at, it goes from between 50 and 65 or so wells throughout the watershed, typically on a quarterly basis. More recently than this map, the different groundwater management agencies, they collect data at a much higher frequency, and much of that data falls outside of our calibration and validation period, but there is some transducer data within our calibration period that we also look at. But going back to 1993, the data that we had, we established this potentiometric or groundwater elevation contour map. And that's what this contour map shows. And it shows what is logical, that as you get closer to the ocean, the groundwater elevations approach sea level. And as you move up the Ventura River, and the ground surface elevation moves up from about, all the way up to about 900 feet or so. And the groundwater elevations along that main stem are, increased to about 800 or so feet along that. And then, of course, as you move up in elevation and to much higher elevations in the upper Ojai Basin, for example, you see these groundwater elevations increase, and we see groundwater that would tend to flow a similar direction as surface water, and ultimately flowing southwards towards the Pacific Ocean. And so this is what we use to establish the initial conditions for the groundwater elevations in the model. And there is a model spin-up period within the first 6 months to a year or so, depending on where in the domain, as these initial conditions are brought into equilibrium with the assigned parameters. But we found that using this measured data provided a pretty good establishment of these conditions within the simulations. But for the bedrock areas, which is really the rest of this watershed, there is much less groundwater data. And so in that case, we've actually have a slightly iterative approach where we have water years within the validation and calibration time periods that are similar to the year preceding the fall of 1993. And we actually use those simulated results to establish the initial conditions in the bedrock. And we've found that helps to reduce the time of this spin-up period. Okay. So moving on to the boundary conditions, this is a map of the watershed, and it shows the key groundwater, some of the key groundwater boundary conditions. I'll discuss some of the others in a couple slides. So these boundary conditions are assigned, and in some cases, levels are calculated based on parameters that are assigned to each of them. And these are areas that have interaction with groundwater on the edges of the domain, of the groundwater portion of the domain. So, for example, the easiest to explain is the Pacific Ocean. We've assigned a constant head boundary there that is a salinity adjusted and based on the mean sea level of the closest gauge in the ocean there. So it's close to zero mean sea level. And we also have a variable head boundary in the upper Ojai Basin on the watershed boundary here. So this blue is the watershed boundary, and the Ojai Basin is unique in the Bulletin 118 basins because it straddles that boundary. So there just happens to be two groundwater observation wells that are located right at that boundary. And we use those to establish a variable head boundary at that portion of the domain. Everywhere else, it's assumed no flow. And in a couple portions of the domain, we've established a horizontal flow barrier. This is a package within ModFlow that reduces horizontal flow. And a perfect example of why you would need that would be the subsurface dam at Foster Park. We've looked at historical mapping of the extent of that subsurface dam, and we've established a horizontal flow barrier based on that. And also the Santa Ana Fault on the edges of the, at the southern edge of the Ojai Basin, we found that it was helpful to actually establish a horizontal flow barrier there as well. And then the other two on this map I'll talk a little bit more about are the lake, what's called the lake package, and the Streamflow routing package. So the Streamflow routing package is how GSFLOW handles all Streamflow river. And so this is all tributaries, all streams, and the Ventura River itself are all handled with the Streamflow routing package. And so all of the results, for example, that Al was talking about in comparing the simulated results and the observed are coming from the Streamflow routing package. And so briefly, what is represented by this package are all the inputs and outputs that can happen in any cell. So the stream dimensions are established within each model cell, and then the model parameters are associated with each of the stream are assigned within that boundary condition within that cell, and then as well as diversions into or out of that cell. And then the model calculates a stream flow rate and elevation. And so all the inflows to a stream would include surface runoff, tributaries, a diversion into that stream if there's one present, and then interflow in the soil zone of PRMS, and then areas where there's groundwater discharge and direct precipitation. And then everything out of a stream would be if there's a diversion out of the stream, if there's direct evaporation, although it's not shown on this slide, evapotranspiration, diversions, and then stream leakage into the aquifer. So all of these different processes can be simulated and are simulated. And this is just a kind of callback to Al's presentation. This is an example of the end result of the streamflow routing. It's a simulated stream flow rate and elevation, and the model then also simulates groundwater interaction as a part of that. And so it does have bearing on groundwater elevations. If, for example, we have groundwater discharging to a stream, that discharge rate is going to be sensitive to the elevation of the stream, the width of the stream, and the hydraulic conductivity of the stream bed. And so if we change those parameters in groundwater calibration, that also has an impact on the simulated stream flow. And then the next is the lake package. There are two lakes in the watershed. There's Matilaha Lake and Lake Casitas. And the way this works in GSFLOW, again, is we do not assign a lake elevation that changes over time. The model actually calculates that. What we do is we assign all the inflows and outflows and parameters that the model then uses to calculate that. So, for example, if there's diversions, or, into Lake Casitas, which there are, we represent that. If there's flow into the lake, and any groundwater interaction with that is based on the conductance of the lake cells. Precipitation, evaporation are also calculated. But we do look at, when we're looking at the model and how it's performing, we do look at the simulated lake elevation that comes from all of those calculations. And obviously, we want to make sure that the lake elevations are being represented correctly. And so this is a comparison of the measured elevations at these two lakes in the current simulated in the preliminary calibrated runs that we have right now of both Lake Matilaha and Lake Casitas. So we see a pretty good agreement. And so that is a check on the boundary conditions that are assigned there. And then the last and very important boundary condition is the wells. And this came from our last webinar. Al spent an entire webinar discussing all of the voluminous work and resources and data that went into calculating really this map, which is our best estimate of the pumping rates that based on, in some cases, measured or reported data. For example, within the Ojai Basin, there are many wells that are metered and report those pumping rates to the OBGMA. There are some wells in the basin that report groundwater extraction based on an assumed evapotranspiration rate and land coverage for their crops. And most of the municipal agencies have a lot of reported of data on their pumping rates. So we're not really guessing at that as much. And they provided that to us. And then, of course, a lot of what Al went into was then, the estimates that were made and all of the checks that were done to make sure those were reasonable for the agricultural pumping and the domestic well pumping. So that's really what's shown here. And this is an average pumping rate map. But as Al talked about in the previous webinar, we do make assumptions of how those pumping rates change from year to year when data is available, and also within month of any particular year. So these rates are not constant. They do change quite a bit over the years. And as Al talked about, a lot of that is driven by changes in the climatic conditions that are captured in the ET rates that are used in the water balance that he presented. And then within any particular year, it's also not just a constant pumping rate. So we use both residential and agricultural monthly factors to represent these pumping rates from every month. And so I guess this is an important point, that the stress periods of the GSFLOW model is months. So things are assumed constant within any particular month when it comes to pumping rates, for example. Okay. I don't have a question slide, but I know I've gone through a lot. So Kevin, if there's any questions that have come up, I'm happy to take a break here and go over them.
Yeah, let's take a beat. Thank you, Greg. Any questions? I don't have any in the chat yet. I don't see any raised hands. But okay. Give folks maybe just 30 seconds here to type something down if they wanted to ask one.
Okay. I'll let you tell me when to move forward, Kevin.
Yeah. Okay. I'm not hearing anything. I'm not seeing anything. Yeah. Why don't you please continue?
Okay, great. So the last topic here is similar to Al. This is sort of a cultural merging between the surface water modelers and the groundwater modelers. And we have our own kind of statistics that we've found to be over, the many decades of groundwater modeling are the most subjective ways objective ways of trying to evaluate the quality of a model. And so there are 3 that are primarily discussed in our study plan. And I'll discuss those here and discuss, how we use those. And I'll use this example hydrograph to illustrate those. And this is a little, this is one well that's observed in the watershed, and it's located along San Antonio Creek, very close to the confluence with Ventura River, and very close to gauge 605. So it's just an example, and I'll talk about each of these. So, there is professional judgment and review of individual hydrographs that I think is a really important part of model calibration. But like I said, we do like these objective statistics. And so the first is the mean error. And this is a simple average of the residual error. So for every single observation point, and again, this is quarterly data for the most part collected over many years. So there's lots of data points that are collected. And again, this is primarily by Ventura County that's collecting this data and provided it to us. So at every single one of these points where they go and they gauge a well, there's also a simulated result groundwater elevation on that day. And so for every single time there's that measured value, there's also a simulated value, and the residual error is the difference between that observed and simulated value. And the mean error is just a simple average of all of those residuals. And so it's helpful, but it does have a drawback, and that's why we have other statistics too. And what this really provides mostly is an indication of the model bias, because if you have lots of positive, very large residual values and lots of negative ones, they would cancel each other out. And you could have a mean error of 0, which would look great, but you'd have wild fluctuations around the data. So that's why we have the other statistics, but the objective of the mean error is really to indicate bias. If we have a very large positive value, it means the model is preferentially higher than the data. And if you have a negative value, it means it's preferentially lower than the data. And so, for example, for this well, we have a mean error in the current simulation of negative 0.8 feet. So, we like to get that value. The objective is to get that value as close as we can to 0. In this case, it's less than a foot, but it is negative, meaning that, very slightly, the model is biased a little bit low. The next is the root mean square error. And really what this is it's like an absolute value. It's analogous to an absolute value of the residual error. So now the positive and negatives are both looked at as positive values. So this is really a measure of the average difference between the model and the observed data, but it's always positive. It gives no indication of bias, just the total absolute error. And in this case, the root mean square error for this well is 5 feet. And the correlation coefficient is the last of these three parameters. And this is the measure of the linear correlation between the simulated and observed groundwater levels. So instead of plotting up as a time series chart here, if you just plot an XY scatter plot, this would be the correlation coefficient between those two data sets. And so it's the square root of the R squared, if you're familiar with the R squared. And so whereas the R squared value is always positive, the correlation coefficient actually can vary from -1 to 1. And a value of -1 would mean a completely perfect negative correlation, which we would not want to see here. Whereas a 1 indicates a perfect positive correlation. So in the project study plan, we established very specific goals related to these statistics for the groundwater model. And what we said is, there are objectives, and this is copied straight from the project study plan. The objective was to bring the mean error as close as possible to a value of 0, and bring the R value as close as possible to 1. And of course, when we're calibrating and changing, we want to use model input values that are consistent with the observed data or realistic estimates. When it comes to the root mean square error, that is typically scaled in a groundwater model. And when we say scaled, that means we actually divide that root mean square error by the range in the observed results. And so that scaled root mean square error is then provided as a percentage. And the standard in groundwater modeling is to achieve a scaled RMSE less than 10%. And so that's what we had in our study plan. So these are the two very specific goals we had in the study plan. One was to bring the scaled root mean square error to less than 10% for each individual groundwater basin. So as an example, if the total observed head change in a basin is 400 feet, meaning from the lowest elevations you see in groundwater wells that are actually observed in a basin to the highest, you had a range of 400 feet. That means that our goal would be to bring the root mean square error less than 40 feet, so less than 10%. And then the second criteria came directly from the California Department of Water Resources Best Management Practices for Groundwater Modeling Guidance that was written really more as a guide to the SIGMA program. And the one quantitative statistic that is really mentioned in that guidance is to achieve a correlation coefficient greater than 0.9. And so we set that goal for each basin individually to reach that correlation coefficient. Okay. So just like Al, I'll kind of talk about why all of these statistics allow for the calibration not to be perfect. And no groundwater or surface water model I've ever seen has a near, perfect calibration. There's always going to be some residual error, and that's why the R value can be 0.9, and that's why the scaled RMSE really should just be less than 10%. And so there are a lot of, there are several data limitations here as they're typical of this type of watershed. So this is the list of some of those that I think are key and have some impact on our ability to achieve the calibration. So one is that most of these observation wells are also actively pumped supply wells. And that means that in some instances, the observed water levels actually may be influenced by wellbore effects from active pumping. And so the observed groundwater elevations can actually be biased low because of that compared to the adjacent aquifer. Even though we went through this entire water balance approach to try to estimate pumping rates, that was really a regional scale analysis. And it is the most comprehensive analysis by far I've seen in the watershed, what Al went through on our last webinar, but it is a regional scale. And so individual pumping rates at any individual well, there's error associated because we had to estimate those pumping rates. And the groundwater elevations that are observed are heavily impacted by those pumping rates. So if our pumping estimates are off at any particular well, that's why the simulated results may be different than the observed. The pumping rates, particularly in the Bolton 118 basins, have a very significant effect on groundwater elevations. In addition to that, the well screen intervals for both pumping and observation wells are often unknown. So even some of the observation wells that we have data in groundwater elevations, we actually don't even know exactly where they're screened. And we have to make best estimates of that vertically. And that's also true for many pumping wells. We don't know where they're screened. We don't know exactly what vertical interval they're pumping from. So again, we have to make some assumptions about that, and that could lead to some error. We do have month-long stress periods, meaning the model pumping rates are assumed constant throughout a month. These observations are from any particular day within that month. And so that there can be variability within a month, and we've had to average along that month, and that can be another source. Any uncertainty in the geologic analysis that we presented to webinars ago, and the model layering and the zoning that came after that, and several necessary simplifications in that model layering. For example, the geologic analysis is based in some areas of the watershed, only information that's available are driller's logs. And so that could be a source of uncertainty in the model. We have 330-foot model grid cells, which are really required for a model of this spatial scale. I think as Al mentioned, the model runtimes are about 15 hours, and that's directly related to the number of cells in the model grid cell size. So a local model that's for one of these particular basins, or a smaller area of one of the basins, would have much smaller grid cell sizes. Because of the regional nature of this model, we have these large grid cell sizes, and that means that certain features like topographic surface are generalized over that 330-foot square area, and that also, any particular wells that are located within the 330-foot area, that pumping is all, assumed combined within that one cell. If there's an observation well that happens to be in that same cell, it's driven by the pumping from those wells. So there is some generalization just based on the model grid cell size. And the anything, and then I'll just say that anything that Al talked about in terms of the limitations for the surface water model, of course, would also carry through and propagate to the interaction of the groundwater model and the surface water model. And the same is true vice versa, that anything on this list really would have some impact on the surface water modeling to the extent that surface water and groundwater is exchanging and impacting the stream flows. Okay, I do actually have a specific question slide here, so I'll stop again.
Anyone? I don't have any questions in the chat. I don't see any raised hands. So we'll give people 30 seconds here just to let us know that you have a question. If you're still kind of writing it down, you just type a letter into the chat and we'll wait for you. Something like that. Thank you, Greg, for the presentation so far.
Sure.
So looking for questions, any thoughts, impressions, questions, comments? Okay, gone. Okay, please continue.
Great. So now we're really going to start talking about the preliminary calibration results and where they're at. So I'll talk first about the hydraulic properties that have been assigned as part of that calibration. Some comparison to aquifer test results. And other data on some of those hydraulic properties in the basins. The statistics by basin. So the exact same calibration statistics I just talked about, we'll talk about each of those for the model domain as a whole, and also broken out by the different basins. Pull out a one-to-one plot, which is a way that we often look at residuals, as well as a histogram of residuals, which is another typical way of looking at model residual values. So I'm really starting on a larger scale, and then we'll zoom in on individual wells, a map of the root mean square error for all the individual wells within the calibration period. And then I'll show the simulated and modeled results first for about a quarter of those wells. And if we have time, I'll look at another way that we evaluate if the model is performing in a reasonable way, which is looking at the water budget. And then we'll wrap up with Al talking about the next steps for the calibration and validation. Okay. So I'm not, I listed 5 parameters that are the key parameters. I'm only going to talk about 2 of those right now. And that's the aquifer hydraulic conductivity and the storativity. And for the aquifer hydraulic conductivity, this is going to look somewhat similar to that zone map that I showed you earlier. This is the topmost model layer. And these are the current hydraulic conductivity values that are assigned within those zones. And so smaller hydraulic conductivity values are fine grained units, clays, shales. Larger hydraulic conductivities that are in the higher colors here, like the reds and the oranges, are gravels and sands. And so, you see very small values in areas of the watershed outside the basins. For example, in the shale units and the sandstone units are somewhat larger than that. In these alluvial channels in the bedrock areas, we do have somewhat larger values, and there are some wells that actually pump in these areas. And so, we make sure that the pumping that can be achieved that we assume is happening there based on the hydraulic conductivity values that are assigned. And then, within the actual basins, this is really a combination of values that were assigned based on initial data from aquifer tests and other literature sources, and then the process of calibration is really adjusting those. And within the Ojai Basin, it really started from the values that came from calibration of the Ojai Basin groundwater model. And so, for example, this is just one aquifer test result. There's 7 aquifer tests that we have listed in the study plan in the watershed. And most of those, 5 of them, I believe, are in the Ojai Basin from Jordan Keir's master's work. And then 1 that was provided to us in the lower Ventura Basin, and then the Foster Park, there was a series of aquifer tests there done by Hopkins Groundwater, by Curtis Hopkins. And so this is just a comparison. For example, there at Foster Park, Hopkins Groundwater, based on their aquifer tests, had a hydraulic conductivity of ranging from 398 to 1,875 feet per day. The median of the values that were reported from the different tests there was 922. And right now, the calibrated value in that area is 1,000 feet per day. So very close to the median of the aquifer test results, and certainly within the range. And so we actually, really needed to have the hydraulic conductivity be this large in this area to achieve the pumping rates in Foster Park and just kind of match the groundwater flows that are observed there. And I don't have those on a slide, but in the Ojai Basin groundwater model, the previous hydraulic conductivity values were all found to be pretty similar to Jordan Keir's master's work. So that's a comparison for the upper layer. And again, as you move down, the zoning changes, and some of these alluvial areas are thinner. So now the bedrock areas are really what's being represented by the model layer 2. So you see this changing as you move down, just like you did the zones. And as you continue to move down, eventually it's only the Ojai Basin that really has the thickest sediments there. And then the other parameter map that I'll show you today is the storativity. This is a measure of the storage of groundwater within any particular aquifer volume unit. And these values have been subject to change during calibration. Also, they are, the zones, the spatial zones are the same. So, but the values within those zones are changed during calibration. We actually found the storativity of the bedrock units to have some impact on the streamflow at the streamflow gauges that Al talked about in the bedrock areas. So this is a key parameter for the streamflow as well. And it was largely dictated actually by that in the bedrock areas. Within the groundwater basins, there's a little bit of data to compare to. And so, I really like this old study from Turner in 1971. In the upper Ventura, he had values of 0.04 to 0.16. And then in Ojai, he had somewhat smaller values of the specific yield or storativity of 0.02 to 0.1. And, the values that we have, they don't match Turner's maps exactly, but the general range of values is very similar. And so that's just one point of comparison. All right, so now looking at the calibration, the preliminary groundwater calibration. So from all those 60 or so wells, we have about 4,100 individual observations. And there's much more wells and data in certain basins than others. But these are the calibration statistics during the calibration period that Al discussed. And again, our goals were to reach a scaled root mean square error less than 10% and a correlation coefficient greater than 0.9. Although it wasn't listed quantitatively in the study plan, we also want to bring the mean error as close to zero as we can. And so the short story here is that we've met those statistics for each of the groundwater basins, the 4 groundwater basins. The correlation coefficient, for example, is greater than 0.9. It's actually closer to 0.99 or greater for several of these areas. We also have some wells that are outside the basins, a handful of these wells that are within the watershed, but not located spatially within one of the groundwater basins. We've also achieved those statistics for those wells. And if you look at the model overall, we've also achieved the correlation coefficient, 0.99. So that's really good. And the scaled RMSC is also very low. And so, we're happy that we've met all of these calibration statistics. But looking at it on such a broad scale, this can hide variability in the quality of the calibration. Can be better in one part of a basin than another, or vertically. It can be better in shallower versus deeper. So, these are really the objective statistics that we're looking at, but that doesn't negate that there is some additional dialing into specific wells in certain areas. And so that's, really where we are kind of now is, looking past these statistics. They've been met. I don't imagine that we're going to improve upon them. They may even get, change a little bit in the other direction as we really try to address certain key, remaining things here and there within the watershed at any particular location. So another way of representing this, it's a nice colorful diagram instead of a list of numbers, is the 1-to-1 plot, where we're actually plotting an XY scatter plot of simulated versus observed head. And the colors are the different basins and those wells that are outside the basins. And so if the model matches the observed data exactly, it would fall right on this black line. And so what we want to see is, we know there's going to be some scatter around this line, but we want it to be tight around that line and not show any significant bias. And so what one challenging part of this, it's an entire watershed, and anyone like who's on who's gone through the different parts of the watershed know that there's quite a bit of vertical scale as you move from the ocean to the upper reaches of the watershed. And so that's reflected in groundwater elevations that go from all the way from about sea level to about 1,400 feet. And so that's why you see that large range over this whole domain. So this is certainly one very standard way of looking at the quality of the groundwater calibration. Another that I tend to like is a histogram of the residual values. So on this plot, there were 4,100 individual dots, and many of them overlap the others. So you have one big green blob, and it's helpful to kind of see the general spread in the Ojai Basin, for example. But the residual histogram is just another way to look at what is the typical residual value, the typical difference between the model and the observed data. And so this is a histogram of the residuals given as a percentage for all 4,100 individual measurements. During the calibration period, there's 58 individual wells. So the most common, about 24% of the time were between 0 to 10. The next most common is this, is the same on the other side of 0, which is -10 to 0. So for the most common residual values are between -10 and 10, and then it spreads out from there. So there are a handful of values, less than 1% of the time, we might have residual values due to data scatter or model uncertainty that are, out on the reaches of this histogram. But for the most part, the majority of the residual values are within about 30 feet. And the most common categories in this histogram are between 0 and 10 feet. And so this is for the watershed as a whole. As we move forward, we could break out these types of diagrams for the individual groundwater basins. Okay. So now dialing in from like watershed scale to individual areas. This is a map of the observation wells during the calibration period. And it's a color-coded map of the root mean square error for each individual well. So not looking at it as a basin or as a watershed, but actually for each individual well. And so the blue means, the smallest value we have is about 2 feet. And so for 2 to 10 feet, and this is the average over all time periods for any individual well. So 2 to 10 feet would be the closest match. We have some that are on average between 10 to 20 feet. We have some that are 20 to 50 feet and some that are greater than 50 feet. And I'll come back to this. It reminds me of something I wanted to go over actually. So keep in mind, I said that our goal was to reach a scaled RMSC less than 10%. And so for the Ojai Basin, we have a range of 600 feet, and it's actually about the same for the Upper Ventura. So we've achieved that, but that does mean that, given that large range, we do have on average within those basins are, RMSC values that are 30 and 40 feet for those two basins respectively. And there's just a lot of scatter within the data in any individual well in those basins. There's also a large range in surface elevations and groundwater elevations. So we've met those statistics, but just keep in mind that on average, that means that we're up for 30 or 40 feet residual in those two basins. So we're not surprised to see those kinds of values at these wells. So again, this is all of the wells. There's 2 wells within the calibration period that only have 2 data points at each of them. So they're actually not plotted on this map because it's just not representative. All the rest of these have at least several months of data, and many of them have years and years of quarterly data, so hundreds of measurements. And so I'm going to show you some examples, and I've tried to pick out representative. I'm showing you about a quarter of the wells, and I've tried to pick out representative mix from all these 4 categories. And the first kind of set that I'm going to show you, I'm going to move from south to north along the Ventura River main stem, groundwater wells that are relatively close to the river. And I'm going to show you zoomed in hydrographs for these individual wells. But first, I think it's helpful to show a graph that just combines the simulated and the observed for all of the wells that I'm going to show you. So we have, for example, this is a monitoring well that we took data from the State Board's GeoTracker website for a hazardous waste cleanup site like a gas station. And so we have that. That's the one that's closest to the ocean. And so there, as you're close to the ocean, the groundwater elevation's very close to 0. And as we move up in the watershed, the surface elevation rises to about 900 feet, and the groundwater elevations rise to about 800 feet. And so at each of these wells I'm going to show you, I'm just sort of showing you the overview first. And it's important to look at it and keep this spatial scale in mind. And it's really important that the model is generally simulating the actual elevations pretty closely. There's errors, and we can talk about issues in any particular well, but it's also important to note that we are getting the gradient generally correctly. And that is because the model is matching the observed data at this scale over the stem of the Ventura River. So let's just keep that in mind as I move from south to north. So I'm gonna keep this graph kind of crunched down here and then zoom in any particular well. And when I show these individual wells, you also have to keep in mind the vertical scale of the y-axis, because if I made this, from 0 to 1,000 like it is here, you can't really see any difference. And so you can see the amount of fluctuation at any particular well and how that changes throughout the watershed. We've used a consistent value of 100 feet scale on these plots, except for the Ojai Basin and maybe a handful in the Upper Ventura, where even 100-foot scale, the observed data changes more than 100 feet over any particular couple of years. So we actually have to have a larger scale. But other than that, it's a default of 100 feet. So I'm not really going to provide a lot of color as I move through these. I'm just going to present to you the simulated and the observed results. This is an example from a well with the root mean square error close to the ocean there is between 2 to 10 feet. This is a well that beginning in 2012, the county started actually collecting data at 2 wells in the Lower Ventura. And so we only really have that data more recently. The older well, the data that's for the rest of the Lower Ventura is all from GeoTracker website. So this is one of those 2 wells that the county collects data from. This is the production well at Foster Park, or a well that's close to the production wells at Foster Park, rather. Moving north, this is a well I actually showed you previously. This is a well that's outside of the Upper Ventura Basin, but I think it's an important well for us as we calibrate both the surface water and the groundwater domain, because it's along San Antonio Creek near the confluence with the river, and it's close to gauge 605. So changes that we make in the surface water model that could have some bearing on the calibration at the gauge 605 could also have some influence here. So this is one reason why we pay kind of particular attention to this well. There's 2 wells there along San Antonio Creek. This is one I'm showing you as we move north. This is a higher up in the Upper Ventura. This is an example of a well that is in the orange category of 20 to 50 feet. And this arrow is showing where we are on this scale. We're moving north again to another well in the Upper Ventura. And this is an example of, really essentially an exact match almost between the model and the observed data from most years, including this tail end of our calibration period. And then moving to these wells that are on the very northern edge of the Upper Ventura Basin. This is the last one in this kind of transect that I'm showing you. All right, I'm going to do a similar thing here where I'm going to move now from west to east. And from one of these wells that's north of Lake Casitas all the way to the Upper Ojai Basin. So this is one well. And moving to part of what we've been calling the eastern part of the Upper Ventura Basin. This is one of the wells with the higher orange category there. This is, I picked this well out for a reason. There's a lot of fluctuation in groundwater elevations in many parts of the Ojai Basin. And that is very challenging from a groundwater model perspective. But I think it's also important to say that not all areas of the Ojai Basin see that amount of fluctuation. It really depends on where you are in the basin, how close you are to the stream beds. And so it's important to us that we're not seeing the 200-foot swings in this model, that we are in other portions of the domain. So it's not like everything is being simulated exactly the same within the Ojai Basin. And then moving up a little bit, this is one of the green categories, 10 to 20 feet up in the northern parts of the Ojai Basin there. Seeing the simulated results. This is one of the red ones. I think there's 6 reds total in 60 wells, 58 that are shown here, with only 2 data points. So this is it's a little bit less than 10%. So this is one of those where we're seeing the larger residual values there between the simulated and the observed results. This is actually 2 wells that are near each other. And as we move eastward in the Ojai Basin, one reason I wanted to pick these out is just to demonstrate that although there's lots of dots on this map, not all the wells have data throughout the entire period. So this is an example where there's only a couple of years of data there, but still it's part of our calibration. So it's shown here. But there's a well right next to it with a longer term data set. So, obviously in the statistics would be weighted much more heavily to looking at this well. So they're green and orange right next to each other there. And then if you go back through all of these, by the way, you'll see that we're always, because I'm moving from west to east, we're always in about the 600 to 800 feet range in the observed and the simulated results. But then when we go to Upper Ojai, we're moving up quite a bit because ground surface elevation increases quite a bit there. And so, we're no longer in 600 to 800 feet, even though we've moved directly to the west. I'm sorry, to the east. Now we're up closer to like 1,200, 1,300 feet. So there's only 3 observation wells in the upper Ojai Basin. So this is one of those. And then the last well in this series is the one here on the edge of the upper Ojai Basin. Okay. So I think I do have about 5 minutes or so to run through the last part of what I was going to discuss, which is the water balance, which is another way of looking at the model performance. So I'll move into that, and then we can move to questions, and Al can wrap up. So this is these are bar charts of the water balance for every single water year of the model time period. And so the positive values here are groundwater inflow. And this isn't every single component of the water balance, but these are by far the majority of the water balance, both inflow and outflow. And this is for the entirety of the model domain. And we'll break out these graphs separately for the basins potentially, but just looking at the model as a whole, the main inflow component to groundwater is recharge from the soil zone and recharge from the streams. And so you can see that that fluctuates from year to year from somewhere closer to 20,000 acre feet to greater than closer to 100,000 acre feet. And I've also plotted up for reference here just the observed precipitation at the Ojai Fire Station. And what we want to do here is we want to check that at the end of the day, after all these calculations that PRMS is doing, that ModFlow is doing, that we're seeing a responsiveness to the climatic conditions that we would expect. And it's going to be somewhat muted because there's recharge from irrigation. So it's not only driven by precipitation, but we do want to see this kind of responsiveness, and we do. So you see the wettest years like 1998, we see a lot more recharge. And then in these drier years, we see lower recharge values. On the discharge, this is what's exiting groundwater. Again, this isn't every single component of the groundwater balance, but these are the primary ones. We have pumping, and this is for the model as a whole. If we were to zoom into any one of the basins, the fraction that pumping would be of what's exiting the basins would increase. Groundwater ET, and I think there was a question in the previous part of the webinar to Al about the ET, and this is the ModFlow ET package. And that is really the only way to achieve groundwater evapotranspiration directly. And so this is based on the extinction depth that was mentioned and the ET rates that are assigned. And so we do see that. And of course, as was discussed, that can play a pretty important role in the simulated stream flows. And it also has some impact on groundwater elevations as well, closer to the streams. And then also discharge to the streams is the largest component. So except for in the drier years where maybe there's a little bit more pumping than discharge to stream flow, but on average, and it's particularly in the wet years, there's a lot of recharge from the streams, but there's also discharge to the streams. And this is kind of consistent with the classical model of a coastal basin like this, so not unexpected. Just to give an example, we also look at the spatial variability of recharge, and this is a map that is showing water year 1998, so the wettest year in our calibration period, the spatial distribution of that recharge and how that varies spatially. And that is really dictated by all the parameters we talked about, the stream flow, hydraulic connectivity, and the soil zone, access to groundwater rate. And so that's dictated by the parameters that are established for those different zones. And that is really what's driving the variability that you see on this map. But you do see, more recharge in some of the alluvial areas than the bedrock areas. You also see recharge focused in the stream channels in some areas, which is consistent with our conceptual understanding of these basins. So we're also looking at this kind of mapping, and to the extent it's impacted also by the presence of impervious surfaces. And the last part of this is looking at the change in groundwater and storage. So if you'll see on these bar charts, for example, they don't always equal each other. So in 1998, we had about 100,000 acre feet of recharge, but only about 80,000 acre feet of discharge. So they're not always going to equal each other. And the reason for that is because there's changes in the amount of groundwater and storage within a year. And so that difference is made up by an increase in the groundwater and storage in a wet year. So in 1998, for example, we see 20,000 acre feet additional water that's then stored in groundwater. But then in a subsequent dry year, we see, again, there's a difference in here, and there's actually a loss in groundwater and storage. And this really is what's driving the variability of groundwater elevations in these basins. And so we do see that groundwater change in storage mimic the climatic cycle. And this is, I think, my last slide here that indicates, that just if you compare the simulated results in the observed data with these change in storage. So for example, if we look at that wet year, 1998, 2005 was another wet year. You see this increase in groundwater elevations, which the model is doing to achieve this increase in groundwater and storage. So 2005, you see this large increase. And the other end of that, in these drier years like 2007 and during the drought, you see these declining groundwater elevations in the simulation, and that's related to these decreases in groundwater and storage. At some point during the drought, there really isn't simulated any additional change in storage. It's like we've lost what we can, and so that's why you see this kind of flattening out of the simulation there. So, and then in 2017, when we then had a wet year, you see the groundwaters kind of rebound just like the observed data did. So just another way of looking at the model calibration and its performance.
Thank you, Greg. Questions? It's about 11:25. We've got a good block of time for questions here. My wrap-up slides with our discussion of timeline and next steps will take about 15 minutes, but we can take up to 20 minutes here for questions on any of the topics covered today so far. Any thoughts, questions, impressions, comments? I'm actually not seeing anything yet.
Maybe everybody fell off and it's just you and me, Kevin.
Yeah, that would be a twist.
We do have the one wrap-up slide from Al too, just to kind of talk about that.
Okay. Well, yeah, folks, please take some time to formulate some ideas. And Al, why don't you do that wrap-up slide, and I'll get my slides ready. Give people some time to formulate some questions.
Yeah, sure. And thanks very much, Greg. That very, very interesting. Great to see the groundwater results. And I do want to kind of reiterate to everyone, and both Greg and I touched upon it, that it's very much the coupling with the surface water and groundwater is very key. And we are still working to improve the calibration. So this is essentially the slide that I finished on. But we presented the preliminary calibration results. We're actively continuing to work on it. We've probably got a new run, that may be a little better than this now, but things take time to pull into presentations. So kind of the next steps, just going back at, once we're happy with that calibration, and part of being happy with it, we'll be looking at the wet and dry mapping comparisons that we discussed during my part of the talk. Then we're going to do the validation, look at those 4 validation years and evaluate how the model does. And then kind of when we write up the modeling report and deliver the model, we'll also have a kind of formal sensitivity analysis that will go along with it. It's pretty standard to present with these types of models. So I think that's it. Are there any questions that have come through before,
yeah.
Kevin, you kind of pull it up?
Yeah, we've got 3 questions that have come in so far. I just see a 4th. So first question from Bert Handy: how many gauges were used for rainfall for the basin? I'm not sure if you're asking for a specific basin, but Al, maybe you could pull up that slide of rainfall gauges.
Yeah, there were 23 in and around the watershed, most of them in the watershed. Let me share over the top here. I'm on a different presentation, so I will.
Greg, the next question will be for you.
All right. So I've got windows popping up at me here. All right,
You can see your screen.
I need to see the other one again. Okay. Yeah, so 23 gauges shown here. Looks like 2 of them, or maybe 3 of them, 4 of them are outside the watershed. They're kind of on the edge of the watershed. And a lot of the gauges are focused on the flatter areas, the lower regions. I mean, that makes sense in terms of, that's where people are growing crops, so they want to know what the rainfall is down there. There's fewer up in the mountains, and that is where we, use the PRISM data to extrapolate. This kind of blocky data here are the 30-year normal values from PRISM. So we use that data to extrapolate from the gauge data up into the upper reaches of the watershed.
Thank you. We've got 4 more questions, so we're just going to roll into the next one. This is, I think, going to be one for Greg, and then I think actually these next 2 will both be, several of these will be Greg questions, I expect. So from Bert Rapp, the simulated elevations in the Ojai Basin were off by 40 feet. Isn't that an unacceptable difference?
Well, the short answer to your question is no, it's not an unacceptable difference, because the scaled root mean square error is less than 10%, and that is the most common standard in groundwater modeling. So we've met that. That is the standard that is in the study plan. And we also have a correlation coefficient that's greater than 0.9, which is the what's set in the California DWR. So no, I've never seen a perfectly calibrated groundwater model that has no residual error values. There's going to be a residual value, and there's 2 ways that we've looked at that statistically, and in both we've met the calibration criteria that had been established.
Okay.
Greg, could you just add a little bit about the range of changes in elevations in that basin?
Sure. Yeah. So the reason that we have a root mean square error change of 40 feet, and by the way, the Ojai Basin groundwater model, I'm doing this off the top of my head. I was the developer of the model. Was I think somewhere not that different than this, like 30 or 35 feet. It's scaled by a range of 600 feet. So there's a range in all of the observed data in that basin of around 600 feet. And by the way, when we look at that range, we made sure there were no outliers. So it's not really, it's a minimum and a maximum, but it's not like, we did take into account that there could be some outlier, some misappropriated data so we looked at it, and that's 600 feet of range. And so the 40 feet is divided by 600, and that's where we end up with a value that's less than 10%.
Thank you. Next question. If people have follow-up, just write it in the chat or something, and we can maybe circle back to it if we have time. And I'm just going to keep rolling through because there's a few more. From Brian Bondi, it would be helpful to see more information about water balance results specific to the groundwater basins.
Yeah, great. It's a good comment, and all I can say is noted.
Okay. We have a comment from Christian Labor. In the groundwater model, how were riverbed hydraulic conductivity values developed? Are these included as part of layer 1? Was there a sensitivity analysis performed to evaluate changes of hydraulic conductivity that occurs after high sedimentation events? So let's take this one at a time. So in the groundwater model, how were riverbed hydraulic conductivity values developed?
Yeah, again, that's a very good question. And I think I'm actually gonna take the second part first. It's not layer 1. So in the Streamflow routing package, there's a conductance term. So it's actually a separate hydraulic conductivity value for the stream, separate from the surrounding model layer. And I didn't introduce him, but we have Farag Botros. Dr. Botros is doing a lot of the modeling here. And if he's able to unmute himself, I might have him chime in on how those were assigned and changed during calibration. But those values have been changed during calibration and partially in response to improving the surface water calibration. But Farag, do you want to speak to that?
Yeah, so as Greg mentioned, the stream bed conductivity is part of the Streamflow routing package, and we have the same zones that Greg showed for the hydraulic conductivity zones, and each of these zones would have a different stream bed conductivity there. and it ranges in the bedrock units like 0.01 feet per day. It could reach to like 1 or 2 feet per day within the basins.
And that is a static value.
A static value, it doesn't change. Yeah, like there's no way in the Streamflow routing package to allow this value to be changed each time step. So it's been read at the beginning of the model and kept the same value throughout the model simulation period.
So the flux between the groundwater and surface water does change. It's calculated based on the changes in elevation or head between groundwater and surface water, but that conductance term is a static value. And so that does not change.
Okay.
So I think that might answer all Christian's questions.
I think you're right.
Sensitivity analysis, yeah, it's a good question about the sensitivity analysis, and that actually is a very good suggestion to include. I'd have to go back and look at what we already have planned for the sensitivity analysis, but that would be something to include for sure.
Okay. Thank you for that question and for those responses. Next question is from William Cowan. I think this is going to be an OWL question. Can you remind us what the validation years are?
Yeah, so going back to my earlier slides, I won't bring it up, but water year 1994 through water year 1997. And if you recall, that was included a very wet year, a dry year, and 2 normal years. So a pretty good range of different water year types.
Yeah, and as Al mentioned, you're welcome. Yeah, our original validation period was different, and we did change it as there was some TAC and public comments suggesting that the validation years we had picked out had issues, and I think those comments were correct, and so that's why we've changed our validation period. And validation is not presented today, because of all those other topics that we have, but also because we're still working on it. Okay, from Bruce Kubler, what is the rate of percolation from Ventura River into groundwater basin? I assume you're referring to the upper Ventura groundwater basin.
Well, I don't know if you want me to handle that. It's a good question. Yeah, I can't pull out a number for you. In the slides I showed of the water balance, that's the model as a whole. But we can pull out that type of information for any particular reach of a stream flow network, including within the river, within a certain area. So we haven't extracted that from the output for this presentation, so I can't give you a quantitative answer. But it is part of, we could look, well, the one thing I could do is we could actually go back, if you want me to share, I can share, oh, sorry, I can share the map that we had.
Yeah, please do. We got about 8 minutes until I need to launch into timeline.
Yeah, I think this is, can you see my screen?
Yes.
Okay. So the only thing I have in here that could partially answer your question is this map. And again, this changes from year to year. And so this is the map just within this wettest year of inches per year. And you can see, within the larger parts of the entire channel there, it ranges from like 25 to, maybe 50 feet. But there are portions of the river where we see much larger recharge values, greater than 50 inches per year. So this is just one example year. So we could plot it up as a map, zoomed into that area. It's, we could also kind of present these bar charts, but this is for the model as a whole. So we would really need to kind of zoom in on that one area and see its variability from year to year to answer your question.
Okay. So if anyone that's asked a question so far has a follow-up, feel free to let us know. If anyone else has a question, let us know. There is another question here. Will there be another webinar for presenting validation and final calibration results? The short answer is not in this webinar series. I think this is the third and final webinar in this series. And I will be talking shortly about our timeline for the next 12 months. And that will include when we expect to share draft validation and calibration results. And so any other questions before I kind of talk about timeline?
But maybe Al could just add a little bit about the model documentation and this type of information that might be in the model documentation when that's released later in the year?
Yeah, that's a good point, Dan. I think the intent is to write this all up formally in a final model documentation that'll present similar plots to what we've shown here today, and there'll be a lot of more technical writing as well, describing things. Of the final calibration and also the validation period, the statistics, and all the wet and dry mapping. So all these things will be made public in a comprehensive documentation report.
Yeah, and as I'm about to speak to, that will be a draft report that will include a long TAC and public comment period itself with an opportunity to review that material. I'm gonna start this final portion of the presentation. Dan, I can't see the chat anymore once I'm presenting, so can you keep an eye on the chat for me, please?
Sure.
Thank you. Okay. Just gonna take a second here to get this up. Okay. Okay. So with the remaining time here, I want to just share our timeline for the next 12 months. So this slide is just a quick review from webinar 1. So in webinar 1, we talked about the project to date. And just as a quick reminder for everyone, we've had 4 draft documents come out, each with a minimum 30-day comment period. 2 of those documents had in-person TAC meetings. Some of these documents I was able to also give a presentation either virtually or in person to the Watershed Council. Some of these documents we simply asked, we told the TAC that these documents were out. We notified the Watershed Council. 2 of these documents were either revised or finalized. We will not be revising or finalizing the draft data report or draft sensitivity analysis approach memo. So I'm just going to jump into what's coming next in the next 12 months. So this timeline is different than what I shared in webinar 1 and what we anticipated in the final study plan, which was published in December 2019. So we have changed our timeline. And I'm going to tell you about that. So this August, we are going to release the preliminary draft groundwater surface water model. That's the GSFLOW model that you've heard about during these webinars, with a user manual, a very simple bare bones documentation. This fall, we anticipate hosting a webinar to solicit TAC and public comments on the methodology that we're going to use to evaluate scenarios under this contract with the GSFLOW model. In December, we're going to release the draft groundwater surface water model in model report. So that's what Al mentioned earlier. Notice the word preliminary has been dropped from that version of the model. And then in the spring of next year, we're going to release the draft nitrogen transport model and its model report. So there's 2 key changes to this timeline. It's one is that we are turning a memo on our scenarios, on how we're going to run scenarios and how we're going to build them. We're turning that memo, which was going to have a TAC meeting, into a webinar, and we'll still have a comment period. And the second change is that we are separating the release of the groundwater surface water model and nitrogen transport model into a sequence. So initially, we were going to release both models together with one report, and now we're releasing them in a sequence. So I'm going to go into each of these deliverables and what you can expect and how to stay involved. So this August, we're going to release the preliminary draft GSFLOW model and user manual. And the purpose is to release an early version of the model to help modelers, model users become familiar with the tool prior to December, when we're going to release a more refined version of the model with the comprehensive model report. This user manual will be short. It'll basically describe how to run the model, how to view model outputs at points of interest, such as a streamflow gauge or a surface water diversion or a groundwater basin exit point. We'll also include the USGS instructions for running GSFLOW. This user manual will not be comprehensive. It will not describe model inputs, calibration, and validation results. It will not describe how to change model parameters to evaluate scenarios. This is just a tool a way to get the model in modelers' hands and let them start learning how it works. So our goal is to drop this on our FTP in August, and we'll notify you through our State Water Resources Control Board Water Action Plan listserv. And we'll also notify the Ventura River Watershed Council listserv. We'll also directly email our TAC, as we always do. So this format for announcing things, we're going to continue. This will be the same for all of the upcoming deliverables, and this is how we've done things so far. So we're happy to hear feedback on the preliminary draft version of the model in this user manual, but we're not expecting feedback. We're not formally soliciting comments until we release the later version of the model with the comprehensive model report at the end of the year. Also, really want to highlight that we're not expecting this model to be used for GSP development. We're aware that the GSAs in this watershed have had to do their own smaller scale modeling work to answer the questions that they need to answer, and the timing of the release of this preliminary draft version of the model and the timing of the release of our actual draft model with the comprehensive report is not conducive to their schedule. I'm going to move on. So after we drop that on the FTP, this fall, we're going to host a webinar on our GSFLOW scenarios. If you've been following closely, you may recall that we said we were going to write a memo to solicit TAC and public comment on how we were going to build and run scenarios, our methodology for scenarios. And we're turning that memo into a webinar. So as a reminder, we have scope and budget for our modeling team to evaluate 8 GSFLOW scenarios with this contract. More scenarios can be evaluated later by either State Water Board staff or local modelers. So these are the initial 8 that we're having our consultants build and run. So the purpose of this webinar is twofold, just as with the memo before. The purpose of the webinar is to solicit feedback on the methodology for the 4 selected scenarios. So we know we're going to run an unimpaired flow scenario. We know we're going to look at climate change, Matilda dam removal, and we know we're going to do a post-Thomas Fire recalibration of the model for 2018 to 2020. So we want to give people the opportunity to see that methodology and ask questions and understand it and provide feedback. The second purpose of this webinar is to have a discussion and to solicit feedback and data on what the remaining 4 scenarios should be that we are going to have our modelers evaluate. We're highly interested in running a voluntary agreement scenario. We could look at groundwater sustainability plans. We could look at other climate change scenarios. We could look at some version of CDFW's draft flow recommendation. There's many, many options, more than we have scope and budget for. So a key part of this is that we need data. I bolded an underlying data because, building these scenarios takes time. And if, you have a recommendation for a scenario, we also ask for data that you can provide to help us build it. We expect to run this webinar in the fall. I expect we'll be using Zoom again, just like this webinar format. And we'll announce that webinar series using all the same platforms we've been using so far. Following the webinar, we'll have a 30-day TAC and public comment period where we can, we're soliciting comments. We will be available after the webinar offline to have meetings with you to discuss your ideas, your data. I keep going. So in December 2021, we're going to release the draft groundwater surface water model and the comprehensive model report. We're soliciting comments on, we will be soliciting comments on the groundwater surface water model and model report for 60 days. The model report will be comprehensive, as Al described, and it will include one of the 8 scenario results. It will include the unimpaired flow scenario result. And again, those are going to be draft results. This is a draft model and a draft report. Just note that the word preliminary has been dropped. So it's a later version of it. We'll also have training materials, more comprehensive training materials that are ready. And so during the first half of the 60-day comment period, we're going to host a 12-hour training, the beginning of which will be general for the water savvy community, like everyone here. And then the remainder of that 12-hour training will be for modelers to learn how to use this tool. And again, we're not expecting this, the model to be used for GSP development. The timing just doesn't work. If you're following Sigma, the GSAs have to submit their plans to the Department of Water Resources 1 month after this is released. And as I understand it, they're very far along in their modeling work at this point, and we're not expecting this to be used for GSPs at this round. To wrap up, we're going to release the draft nitrogen transport model. That's the MT3D-USGS model and comprehensive model report in the spring of next year. This model report will be similarly comprehensive. We'll include model setup, calibration, validation results, and we'll include all scenario results for the water quality model. I think there are 3, maybe 4 scenarios that are being evaluated. So our goal is to do this in spring of next year, and that will have a 30-day TAC and public comment period with a 4-hour training for local modelers. And if anyone, for the local modelers that want to learn how to use this tool, we highly recommend you attend the previous training, the 12-hour one on how the groundwater surface water model works, because that is going to help you be familiar, learn how to use this tool. So to recap, we have 4 things coming out in the next 12 months, 4 opportunities for engagement. We have the release of the preliminary draft groundwater surface water model with a user manual, which we'll put on the FTP this August. This fall, we're going to host a webinar on scenarios so that you can learn about our methodology for the 4 known scenarios and provide feedback, and then you can help us build the other 4 scenarios that we haven't selected yet. And so that we're looking forward to that feedback and those conversations. In December, we're going to release the draft groundwater surface water model with its comprehensive report for a 60-day public comment period. And that will include the local training, the training for local modelers. And then following that, spring of next year, we will release the draft nitrogen transport model with its comprehensive model report. So that is our schedule for the next 12 months. Are there any questions? I see a raised hand. Go ahead, Brian.
Hi, Kevin. Can you hear me?
Yes.
Thank you. I had a question and a comment. I'll start with well, I guess it's a comment / question. The anticipated deliverable in December of the model and model report, accompanied with a 60-day comment period, that overlaps with the period in which OBGMA and UVRGA will very likely be in the throes of finalizing a GSP and getting it submitted to DWR. And that'll be a very busy time, not only for the staff and consultants of those agencies, but also for the board members who represent many of your key stakeholders in this process. So I guess I'm requesting some consideration for trying to shift the timing of that so that we can be in a position to provide you with quality review and quality feedback. So if you could take that into consideration with your management, we would really appreciate that. The other question has to do with the disclaimer on the slides about not expecting the model to be used in this round of GSP development. That could be interpreted to mean that there's an expectation that it will be used in future rounds. I just was hoping you could clarify whether that's the case or not, because for UVRGA, we've invested significant amount of resources in the development of a basin scale model, and if there's an expectation that we're going to switch to the regional model, we'd just like to know if that's what's being implied here or not. Thank you.
Sure. Yeah, we'll get back to you on schedule. We'll have to think about that. How that will affect our release. We certainly want to facilitate good review. I don't have a good answer for your second question. My understanding of Sigma is that agencies are required to consider all best available information, and we do consider this to be information that is good and will be available on future rounds of GSP development. So we do expect it to be, I guess, considered, but that's something that's a big topic and probably something I can't speak to alone or directly.
Hey, I wanted Brian, could you maybe provide a little bit more detail on your schedule or your GSA schedule? And you said you're going to be busy kind of wrapping up your final plan. And could you maybe just, for other people on the call, like describe when that's due? And also, once it's turned in and submitted, does your schedule relax a little bit, or you still have busy periods, that continue immediately after that?
Yeah, am I still live?
Yeah, I can hear you.
Yes.
Okay. Yeah. So the GSPs are due no later than the end of January of next year. And so, like a lot of projects, you can imagine things will come down to the end. So we'll be very busy finalizing and submitting the GSPs, whether it's December or January. I think it's a safe assumption that we'll be in that process. I can't speak for OBGMA, but I'm just speculating that their process may come down to the wire as well. After the GSP submitted, we would have more availability. We do have our first annual report under Sigma that's required, is due in April. So we won't be, twiddling our thumbs, but certainly we would have a lot more time and flexibility in the use of our time after the GSP has been delivered to DWR, which we know for sure will be done by January 31st. Does that help?
Yes.
Yes, thank you.
Thank you. Are there other questions? Okay. I'm gonna give some people some time to write some questions in if there are any more. So thank you all for participating in this webinar series. If you have technical comments, please submit them by Friday, June 25th. You can email them to instreamflows@waterboards.ca.gov. That's the email address for the unit that I work in. And if you need additional context or help, or you have additional questions, of course, you can look at the meeting materials. So we are posting links to the meeting recordings both on our website, and there's also a link to the meeting recording that will be posted in our FTP. Also in our FTP, there are copies of the slides in the chat log. This is instructions right here on how to access information. You can just take a screenshot right now if you want to. Or if this is confusing, just send me an email. I can help you get access to that FTP and the links to the meeting recordings. In addition, we are available to meet with you. So if you want to meet offline to talk about a particular comment or question before June 25th, please reach out. Sooner the better. We do have some staff who are going on vacation, but many of us will still be here. And of course, we're available to meet afterward too. We're always available. You can always contact us. These are the email addresses for all the water board staff that are involved in this project. And also, this is just a link to our website. I understand you can't click on the link, but you also could just try searching California Water Action Plan State Water Board, and that'll take you to the website for our in-stream flow unit, where we post our documents and our link. That's one place where you can find the links to the meeting recordings. So does anyone want me to go back to a slide? Any other questions about timeline? It's about noon, but I can stick around if people want to revisit questions they were asking earlier.
Well, I'll just jump in and just thank everybody for participating again. You know, over the 3 webinar series, and your feedback is helpful. And I'm just glad everybody could join.
I agree. And we, like I said earlier, we do record, all the questions that people ask us. So if you asked a question either verbally or wrote into chat, we've got that written down and we're thinking about it. So thank you for those too. Anything else? Anything else people want to talk about? It is 12 o'clock. I will probably adjourn this meeting in about a minute if I don't hear anything else.
Yep, looks like people are starting to jump off, Kevin.
Okay. Well, thank you all for participating. Let's save the recording and.
Thank you very much, Kevin.
You're welcome.
Bye.
Great. Yeah, thank you, everyone.
So Kevin, I'm going to stop the recording, or do you want to do that?
I got it.